ஹலோ ஹலோ ஆரஞ்சவினா
தம்பி கேக்குது சொல்லுங்க.
பிபிடி இஸ் விசிபிள்.
இல்ல இட்ஸ் நாட் விசிபிள். உன்னோட ஸ்கிரீன் வந்து அப்பியர் ஆயிருக்கு.
கொஞ்சம் இது கொடுங்க. நவ்
நேஷனல் வெபினார் அப்படின்னு கூடிய ஒரு இது ஓபன் ஆயிருக்கு.
அந்த இன்விடேஷன் ஓகே.
ஓபன் ஆகல.
ஓகே ஆயிடுச்சா? விசிபிளா?
உன்னோட ஸ்கிரீன் வந்து தெரியுது, டிஸ்ப்ளே ஆகுது.
எல்லாத்துக்கும் அட்மிட் பண்ணுங்க.
ஓகே ஓகே.
அண்ணா இன்விடேஷன் இஸ் விசிபிள்.
நாட் விசிபிள். உன்னோட டெஸ்க்டாப்போட இதுதான் ஓபன் ஆயிருக்கு. வந்து ஒரு ஃபோல்டர் ஒன்று ஓபன் ஆயிருக்கு, இன்விடேஷன் ஓபன் ஆகல. நோ. ஓகே ராஜேஷ்.
சார் ஆரம்பிச்சோம் சார்.
Hello.
Sir, please admit participant.
Okay, sure.
Shankar Pandian, sir. Very good morning, sir. A warm welcome. Sir, can you audible? Shankar Pandian, sir. Very good morning, sir. Yes. Okay. Thank you.
Hello.
Yes, sir. Very good morning, sir.
Pandi.
Yes, sir.
Good morning.
Arvind sir, please admit participant, please.
Okay.
There are 5 members are
I'm
waiting
doing.
for.
Yeah, okay.
Can you audible?
Audible.
Very good morning. Please, 5 minutes wait. Resource person are now reading. 5 minutes wait. Sir, Arvind sir, please admit participant, sir.
Okay.
Radhika ma'am, very good morning, ma'am. Ma'am, Radhika ma'am, very good morning.
Good morning, sir. Good morning.
Yes, sir. Okay. Madam, good madam. Very good morning, madam. Sir, Arnachalam, sir. Sir, Arnachalam, sir. Sir, very good morning. Very good morning. Good morning.
Good morning, sir.
Yes, ma'am. Kaudi, ma'am. Very good morning, ma'am.
Good morning, sir.
Yes, ma'am. Yes, ma'am. Sir, good morning, sir. Sir, Arumucham, sir. Arunachal, sir, is it audible, sir?
Yes, you are audible, sir.
Yes, okay, sir. Warm welcome to all the participants. Now, welcome address. A warm good morning to all. It gives me a great pleasure to welcome every one of the micro and nano fabrication techniques and characterization. First of all, I thank Almighty for making me to help forward in whatever I do. I'm grateful our management for encouraging and permitting us to conduct the webinar. I'm indebted our president and secretary for making the what I'm today. I happily welcome to our esteemed Dr. Principal Nagarajan, who is a man of vision. He is a constant support, encourage, achieve the successful technical meet. And I extend my hearty welcome to Dr. A.M. Tony Melvin, Director of Self and Course, for his constant support. I gladly welcome to resource person, Dr. the hero of the day, Dr. S. Varadaraja Perumal, and a technology manager, Center for Nano Science and Engineering, Indian Institute of Science, IISc, Bangalore, Karnataka. Dear participants, a small introduction for the resource person. Dr. Varadaraja Perumal is a highly skilled materials scientist and engineer in nano electronics and nanotechnology. A research field from Indian Institute of Science, Bangalore, Karnataka. He has completed his PhD in physics from NIT Surathkal, Karnataka state. The Master of Technology in Nanoscience from Shastra University, Tamil Nadu, and Master of Science in Physics from AVVM Puspa College, Paridasan University, Tamil Nadu. He possesses 10 to 11 years of research experience in several advanced materials, fabrication, and characterization techniques. The provided technical support to users from industries, IAC, RD, and DS, the national labs, and other academic institutions. Additionally, he has experience in semiconductor device, the fabrication with more than 16 international journal publication, and also lead 17 members technical term in the accomplishing the technical activities for technical documents, characterization project, and also what are the any other project MNCF and CCNCF, and also IAC Bangalore. And the next warm welcome to head of the department, ma'am Gaudami ma'am, Department of Physics, Kamaraj College. The next one, I joyfully welcome to Dr. Muthusendil Pandyan, Research Scientist, SSN College, for the valuable support for this national technical meet. Next, I would like to express my thanks to my educators, Dr. G. Narayanaswamy, Associate Professor of Physics, Kamaraj College, Thuthukudi, and also Dr. P. Selvarajan, Associate Professor of Physics, Adityanar College of Arts and Science, Tiruchendur, to encourage the support and guidance to my PhD successfully. It is because of them I have come to the good position, stand before here. And finally, I welcome to all the participants who are the eagerly waiting to listen to the session. Once again, I welcome to one and all. Very good morning, all the participants. Now, hand over the session to Dr. Varadaraja Perumal. Sir?
Good morning, sir. I'm audible?
Yes, audible. So you continue, sir. Very good morning. Very nice to meet you, sir.
Yeah, sir. Very good morning to all.
Yes, sir, yes.
So, first of all, I would like to thank the organizing committee and Dr. Rajesh for the invitation. So, without delaying, then let me start my session. So, is the slides are visible?
Yes, sir, visible.
Yes, visible, visible.
Great. Okay. So, vanakkam, ellarkum vanakkam. So, myself, Varadaraja. So, already Dr. Rajesh already introduced about myself, and as well as today's session is about micro and nano fabrication and characterization technique. So, I would like to share my experience, what we learned here in IISc and throughout the research career. And we are having many industries, industry user, and as well as patron membership from ISRO and DRDO. And many academic users also, they will come and they will do some fabrication and characterization in our center. So I would like to share my experience, and so this platform is open. I will try to cover the basics about the things, some of the techniques, characterization technique what we are using, and some of the basic fabrication techniques what we are using to make some devices. At the end of the thing, I will try to cover at 11:15 and 11:15 to 11:30. Then what are all the doubts you have, then you can ask. Okay. So before start, I really enjoyed this picture. So most probably, you might have seen this image in your WhatsApp thing. It was circulating in recent days. So you can just observe over here, radio and you want to shoot some videos, calculator and CD, something you want to play, music, something you want to watch some videos and everything. So now, this entire thing, it is in your pocket as a mobile phone. So that everybody so this is a much need of some micro and nano fabrication is coming. Okay, so this is just, it is really impressed actually. So this many things are individually we used in the olden days, and now everything in a single device that is called a mobile phone or laptop or whatever. So how we are miniaturizing the things with the technology of micro and nano things. Okay, so this is some small example. You just see that high performance transistors in the olden days, the people they used it. Now you just see because of the thin film. So thin film means there are less than 1000 nanometer things. What we are telling, it is at the thin film. So there are ultra thin film devices also nowadays. The people are making, Intel and other people, they are making it. So what I'm trying to tell, because of that invention of the thin film technologies, so people are miniaturizing the devices, what and all they are making, diodes, a transistor, capacitor, and all. So then, they are miniaturizing the devices. You can just see that, how small, compact thing we have in our household applications. Okay, so of course there are some nanomaterials they are putting, and they are making the things. So let us discuss all in detail. Okay. So how they are achieving it? Many they have a doubt. For example, if I want to make my transistor, so can I make it as a prototype, or can I make it in a available in the market? So it is not possible. So for example, if you want to make your own transistor, so you need some substrate, so for example, silicon only generally they will use. So if you are buying your own silicon and you are making some transistor architecture, and if you test the thing, the performance may be less. So when you see the literature, the people, they might have mentioned that, the performance of the transistor or diode or solar cell or whatever you are making, it is very high, and what you are making in your lab scale level, it is very less. So you might have thinking what may be the reason for that. So of course, the same recipe we are following it. For example, substrate they are using silicon, means we are using a silicon. What they are following, cleaning, RCA cleaning, or piranha cleaning, and we are using the same thing, or soap solution or acetone washing, everything we are doing. Later by they are having some technical techniques called thermal evaporation, or e-beam evaporation, or sputtering something for to make some thin film on your substrate. The same thing you have in your lab, and you are doing it. But everything making as a architecture and complete device, finally the device is not performing as to the level. There are some reasons. Okay, so which means we need a kind of environment which the air molecules or a lot of dust particles are some moisture and humidity, temperature, everything is a matter there. So we need to create an environment so where these things and all having some less particle or less whatever the things. Okay, so that room we are calling it as a clean room. Okay, so you might have seen whenever the people visiting some big industry who they have a clean room, then you have a maybe many people you might have seen this. In case if you want to see this kind of clean room environment, you are always welcome to Indian Institute of Science. Nanoscience department here we have this clean room facility to make the devices, micro nano devices. We are having some different type of clean room. Every year, open day, March first week we are organizing. So due to this pandemic, then maybe coming year it may not be there. So maybe whenever the situation goes off, then you are welcome to visit our center in an open day, because that particular day then it is completely open to all. you can have a look like how the clean room they build and what and all the equipments are there inside and all you can see. Okay, so quick introduction about the clean room. It's a controlled environment that has a low level of pollutants such as dust, airborne microbes, aerosol particles, and chemical vapors. Okay, so completely we are we can just see here that there are Teflon, the holes are there actually. So there are upstairs also there are things. It's airflow. Continuously we are flowing the air. There are some multiple filters will be there that will filter your particles. So which is coming from different dimensions. So here you can just see it's a table. So ISO 1 class 1 and class 10 and class 100 and class 1000 and all is there. Class 10 is a thing that generally the Intel people they will use to manufacture the class 1 is also available. Okay, so that means completely we are eliminating the particles. Means 0.1 micron thing, then there are the 10 particles you can see, and 0.2 micron there are 2 particles only there. So that kind of environment they are creating and they are manufacturing that devices. What all we are using in your mobiles and laptops or wherever that electronic applications or appliance you're using. So everything is made by this kind of clean room environment only. Then only the device will work. Okay, so how much cost it will be? If you want to build that class 100, I need some crores, 1 crore or 2 crore money to build that small room. Okay, so imagine class 10 and all you want to make, then it definitely needs some nearly 10 crore to 100 crore actually. So it's a completely budget oriented, and maintaining the things also it is a highly challenging one, because some of the things generally humans are the contamination, you know very well. So many people in abroad they're using the robotic things because even sometime class 1, class 10, so humans are not allowed inside. So then they have to send that robotic thing to complete their work actually. You can just see there are some bunny shoot. The people they are wearing the bunny shoot and they are entering and they are doing some activities. So this bunny shoot it is protecting what and all the cloth you are wearing, and you can just see here that lab shoe covers are there, and this bunny shoot is there, and face mask and goggles if it required, and hairnet will be there, followed by completely you are covering and you are exposing only to your eye region. So that is much needed when you are entering into the clean room, because if something is got contaminated, the device may not perform well. Okay, so what I'm trying to tell here, the summarizing this slide. So we need some environment where the pollutants of the dust and airborne microbes and all having very less counts. Okay, so completely agree, because most of the people 90% of the people they are not having this facility, but this is also available. If you want to make a real good devices for your project or something, then you can propose it. Of course, what and all the equipment available outside, the same thermal evaporator or sputtering thing what you want to make, there are some diffusion base there, wet etching and dry etching base and all is there. Compared to outside in that environment what and all you're keeping, the cost will be much higher than what you are doing inside the clean room. So that's what I want to bottom line in this slide. So next thing is that let us move a little bit inside to the deposition techniques. So thin film, as I told, miniaturizing the device. So nothing there are some thin film only is there inside. Okay, so there are many ways to make the thin film on your substrate or what and all you want to make over that. So physical technique is there. We are calling as a physical vapor deposition technique, and chemical based. We can make the thin films, and wet based also we can make. So wet based or solution process based we can. So we used to call as a PVD, CVD, and SBD. SBD means a solution process technique. Okay. So what is the main difference? So there are a variety of things are there. Depending on what you have, then we can make some quality of the thin film in a better manner. So generally, if you want to make some devices, prefer to go with the physical vapor. That will be much more reliable, repeatability and all you will get. So for example, evaporation techniques. So it's a kind of resistive heating things. So where you have your crucible, obviously we need a board kind of thing, crucible kind of thing to hold your material. Then when you're thermally resistive heating, if you're doing over there, the material will vaporize and it will deposit into that substrate region. Okay, so of course we need physical vapor deposition consistent with the vacuum. So high vacuum and ultra vacuum is there. Otherwise, the mean free path, it is much needed for the PVD technique. So if some of the things are air molecules are there inside, it will go and bombard, and it will contaminate. The contamination only it will go and deposit as a film. Okay, so physical vapor deposition, it is much reliable than other thing. Let us compare one by one. And evaporation is nothing but just putting some material, resistively heating and evaporating and depositing over the substrate in a vacuum environment. Next thing is a sputtering. So sputtering is a bombardment technique. Like, we are using some inert gases and we are applying a power, either it is a DC power or RF or pulse DC. So when you are applying that biasing, when you're applying a power into that, you are ionizing that things, that argon or what and all we are purging over here. So we are ionizing the things. So the ions, the inert ion, it will go and bombard with your target material. Target means what you need to deposit. For example, copper you want to deposit means we need to keep a copper target. Aluminum means aluminum. Copper oxide means copper oxide, like that. Okay, so when you're keeping the thing this ion, it will go and bombard on your target material, then it will go and deposit over that substrate region. Okay, so that is called sputtering. There are many branches are there actually. So evaporation means there are thermal evaporation is there. So then next thing is the electron beam evaporation is there. So when I'm discussing about the thermal and electron beam, in which case we have to use what kind of technique, then we will discuss in detail. Okay. So the next thing is that complementary for physical vapor deposition is the chemical vapor. So the CVD and the plating, something and all we mentioned. So what is a CVD means? Like it's a chemical vapor deposition, of course, as I told. So what they will do mean they will create some high temperature, generally they will use some reactors needed for this. So for example, if you want to fabricate your graphene or MOS2 or WS2, so over the reactor, you will take a precursor over the flow of some gaseous environment what you want to make. So that will be reactive with the temperature, then it will produce some film. So that is the CVD process, but it required some particular reactor and as well as temperature. And environmental friendly means it's a little bit tricky because if you are not having any proper exhaust thing, then obviously it will contaminating the environment. So CVD thing generally it is useful for some graphene based things, because that which we cannot able to prepare by using the physical and weight. So some special application and special materials obviously we need to stick with that CVD process. Okay. Next thing is a wet. So it is mostly 90% of the people, even for my PhD, I use that solution process thing only. The reason it is very, very cheap. So for example, zinc oxide you want to make. So what generally what people they will do means zinc oxide nano rod or nano tube or whatever. So they will mix with the precursor and they will put it in a hot plate in a hot air oven. So then over a period of time, you will get that nanostructures. So that is we either we can make a sol with that, we can make a gel over there, or the hydrothermal process, or whatever the things which we are doing with a solution based things. For example, Silar technique is there, and dip coating or whatever you want to do, then that is falling in that third category. So spin coating, I forgot to tell the spin coating. It's the simplest technique. So many people are doing the DIY, which means the do it yourself thing. So they will there are many YouTube videos are available. If you want to go through it, you can do it. Why I'm telling this means some of the material you want to optimize, you're not having any funding for that. There are some CPU fans are available. Take the CPU fan, or some motorized fans are available. So just nothing but we are rotating that substrate with respect to that some particular RPM, and there we are pouring our solution precursors, what and all we need to do. Just spin coat it, just spinning and making. Of course, there are many parameter, viscosity, and there are many things are there. Conditions apply. So then simplestly you want to make your device, then you do this, and after that post spin coating, then if you are putting into the hot plate or there are some hard surface, then definitely you will get a thin film. Okay, so spin coating, it is a very coating maybe someone audio.
Please participant, please unmute mute on your audio and video, please. Sir, now okay, continue, sir.
Okay, sorry. Okay.
Sir, no, nothing, no problem. Continue.
Okay. So dip coating, it is a wonderful thing. If you're not having this, all the fancy stuff, then no need to worry about it actually. So dip it for some time. Most probably you might have tried, because I'm not telling the new thing. So many people they already aware about the thing. So to make the thin film. So Silar technique and the dip coating, it is almost complementary. So dip coating means just dipping it for some time, and over a period of time with respect to the time and the precursor concentration and volume, whatever the thing. Then after some time, when you take that thing, the layer coating will be there over the substrate of over the surface of your substrate. Then put it in the hot plate, and thin film is ready. Okay. So the summary of the slide, thin film technology. it's a wonderful technology. And how to attain the thin film technology, like how to attain the thin film, there are many ways are there, complementary ways are there. Physical vapor deposition, chemical and solvent are based thing. So physical, there are many things are there, evaporation and sputtering thing, and the chemical CVD and plating technique is also there. And wet thing is the solgel or like printing, whatever, inkjet printing. So it's a kind of printer technique. So if you're not having anything, you have an old inkjet printer, so nothing wrong. You can try with your own inkjet printing to make the thin films. Okay, so quickly, like I took two deposition techniques. One is a thermal evaporation, another one is a sputtering. So this one, what you're seeing over here, it's a thermal evaporation. So here you can just see here, this is your source material, and here that filament current applying things and all is there. And over here we are keeping our substrate, and generally there will be some shutter in between. The shutter, it is nothing, it is much needed always. So whenever the people are not having in their own system, so prefer to keep the shutter. Otherwise what will happen, like when you are evaporating the material, it is reaching some particular thickness. Of course there will be some quartz crystal monitor will be there to monitor your thickness. So there are tooling factor is there. I don't know how many people are following. Of course, that 90% of the people, they are following the tooling factor when you are operating the thermal evaporation. So it is nothing but like the distance between the source material to that substrate region. That factor we are calling it as a tooling factor. Of course, its conditions apply with respect to the distance between the quartz crystal monitor also. So actual thickness, which will be measured by your quartz crystal monitor, divided by that what thickness you are attaining your material post characterization. Into 100, that is generally tooling factor. Try to create as much as possible, means 100% is a maximum thing, then 98% above it is acceptable. So sometimes what the people they are doing 20%, 30% thing means you are wasting your source material. At the same time you are not exactly measuring the thickness what you are looking on your material. Okay, so tooling factor things, keep the point in your mind. Okay, so source material we are taking over here, we are electrically resistive heating we are doing over here. Then the material once it is crossing, there are some conditions apply here. So all the materials I cannot evaporate, so very well. So there are some conditions. So vapor pressure, so we should know about your material impedance and density. Before you are taking any material for this kind of thermal evaporation thing, so you should know these two parameters. So what is the density of the material and what is the impedance, how much impedance you have to apply, field apply, then the material will start to evaporate. Okay, so for example, metal is there, of course 100% we can, but not all the metals. For example, if you want to deposit aluminum, there are some crucibles are available, filaments are available. You put your aluminum there inside, and maybe I can switch on my video. Maybe you can see my actions, what I'm doing. Okay. Okay. So what I'm trying to tell, there are some density and impedance thing as I told. So apart from that, if for example, if you want to deposit aluminum, there are some filaments are there. So in the filament, you are putting your aluminum, and when you are applying a current, what will happen? This filament, it will get hard first. So then with respect to the material density and that impedance thing, it will start to slowly evaporate the thing from your source region, and it will deposit onto the target. Okay. So what kind of board we have to choose, or filament we have to choose, that is really important. So there are some many crucibles are available for thermal evaporation. This is a filament, generally we're using it for them. If you have any source material as a wire, or some sheets are there, you can. Or if you have some material as a powder material, for example, organic material you want to deposit, there are some boards, the cuvettes kind of things are available, crucibles are available. So there, you can pour your material, you just start heating slowly. So when you start heating slowly, then it will vaporize and it will go and stick onto the substrate region. Okay, so conditions apply. All the materials, as I told already, we can deposit in the thermal. For example, if this material generally it is made by tungsten or moly, so molybdenum boards. So if you want to deposit a molybdenum or tungsten, if you're taking that crucible as a molybdenum or tungsten means, it is not possible, because the reason we are using this crucible, that melting temperature of this crucible is more than 2000 degrees Celsius. Okay, so that is a criteria to choose a board material or crucibles for your thermal evaporation. Okay, so if I want to deposit a moly, it is not at all possible by using this thermal evaporations. So for example, very well molybdenum is one of that top electrode which we are using it for some optoelectronic applications. So what is that alternative way? For example, if I have a zinc oxide, so I have only thermal evaporation, can I do some deposition of metal oxide or dilated material in the thermal evaporations? Of course, it is not possible. Conditions apply. So the reason that molybdenum trioxide can be done, because sometimes the people they are trying it. As I told already, the melting point, it is a matter for this thermal evaporation. So what and all the current value which you are applying, so up to 1200 degrees Celsius or 1000 degrees Celsius, some materials are there, we can definitely evaporate into that. Oxide materials means we need some more power, or we need some more current to evaporate the things. So that is not possible, because sometimes it will break, or it is not possible by using this. There are some complementary techniques are available. That's what I want to tell. So that is called E-beam assisted thermal evaporation, or E-beam evaporation. So what they will do means, instead of this current applying heating that terminal, so they will use the electron beam. So electron beam as a assisted thing, below of your, they will use a graphite crucible. So put a graphite crucible which is having some more melting point. So then below that there will be electron source will be there. This electron, it will, because there will be some magnetic field that will be controlling, that will be focused on your source material. So that electron beam, it will be coming and heating. So that is vaporizing the material and depositing, the technique called E-beam evaporation. Okay. So thermal evaporation is one of the techniques generally that 90% the people they will use for the deposition of electrode. At the same time, E-beam evaporation is a complementary technique. Along with your metals, we can do some metal oxide as well with assisted of electron beam. Okay, so that's a point. So you just see over here, this is that thermal evaporation thing. So here the filament current will be there, and of course, as I told you, we need to create a vacuum. So generally the people, they have a rotary vacuum, rotary pump to reach -3 torr. Then followed by the rotary, then people, they're having a diffusion pump. So diffusion pump is one of the higher vacuum pump. So with the help of that, we can attain that -5. So many people, what they are not having means a liquid nitrogen trap. So liquid nitrogen trap, when you're diffusion pump, it is getting hard, within 45 minutes, then you are not getting the vacuum of -5. You want to do the deposition at -6. So pouring the liquid nitrogen, the trap, which is surrounded to that DP, diffusion pump, then it will cool down, the condensation will happen more, then more sucking things which will be there from your chamber. So there are molecules and what other things, it will go off -6 torr, -6 millibar pressure, then it will be there. It will be good vacuum to do some deposition of your thin films. Okay, so generally, they will use a diffusion pump. So the drawback is that oil backstreaming. Sometimes what will happen, that oil level, it is not maintained properly, or so there are some issue with the diffusion pump, because after lockdown the people are starting their work, so moisture and many things are there actually. So this guy, what will happen, that it will go inside the chamber, backstreaming, it will happen. So that backstreaming thing, it will go on, that oil deposition may happen on your substrate regions. Okay, so there are advantages there and disadvantages also there when you use a diffusion pump. And what nowadays the people, they are, if it is a cost effective actually. So thermal evaporation, if it is a budget constraint, then definitely 5 to 10 lakh, then we can get some portable thermal evaporation. But pump, if you want to replace with the diffusion pump with the turbomolecular pump, of course, turbomolecular cost itself, it is 10 lakhs. Okay, so if you have a budget, then you can choose your pumps, whatever you need. Diffusion pump taking for 3 hours for pumping, then you can do some the turbomolecular pump. If the budget is there, then within 30 minutes, then you can attain the -6 torr pressure. Okay, so the concept of the thermal evaporation to make a thin film is it's a resistive heating. Just heat the guy, and the material what and all you are taking here, and it will vaporize, and solid phase to liquid phase sometime, and directly liquid phase to sometime it is a solid phase to vaporize also may happen. So solid to liquid to vapor, or solid to vapor. So then that guy, it will go in the vacuum, because of the main free path is perfectly fine, then it will go and deposit as a film. Okay, so the quick thing is what I want to tell you, people who already know about that thermal evaporation, what they need to do means HT and LT. So many people they know, but if people are not knowing, I'm telling this. HT and LT means high tension, low tension. So low tension means high current, low voltage. That generally we are using it for deposition, thermal evaporation, nothing. And HT is nothing but it's a high voltage and low current. So what is the need of this guy means, it will create a plasma inside. So this plasma, it will clean the chamber. For example, you are doing your own sample, perfectly fine. Place here, we are allowing all kind of samples. So that it will contaminate the chamber heavily. Or sometimes if you are bringing the substrate from a different environment, and you want to clean the substrate. So this HT mode, it will be really useful. There we can clean the substrate and as well as the chamber. Okay, so this is the HT and LT mode. Which is there in our thermal evaporation. Okay. Okay, so sputtering technique, it is another complementary for thermal. I can tell for metals actually, but metal oxide, this is one of the best technique in the world. Okay, so E-beam is a complementary for this. Okay, so what is sputtering? As I told already, there are some ionized inert ions coming and bombarding with your. You can just see here bombarding with your substrate. So this bombardment, it will eject the target materials. That ejected target atoms, that material atoms, it will go on deposit as an epitaxy layer deposition. It will go over the substrate. Okay, so that technique is called sputtering technique. So of course, here also we are doing it a vacuum. So this is that sputtering technique. So generally, what they will do, they will create -6 vacuum, -6 star. So generally nowadays sputtering, it is coming with the thermal evaporation. So there, we are creating -6, and when you are allowing the argon gas, what will happen? Inert gas inside, what will happen? Then it will obviously reduce that deposition pressure to -3. So sometimes what the people, they want to create some plasma inside, because ionization is nothing but it's a plasma. So plasma, I think they want to get, they want to play around with that power what they are applying onto the terminal, or they want to play around with the pressure is also matter actually. So -3 tar, it is a good deposition pressure. -2, -1 means so then you may not get the quality of the film, because you're completely, you're near to your atmosphere, you're doing the pressure. Sometimes people are making a mistake. That's what I'm pointing it out here. Okay, so its sputtering is widely used for versatile applications. So it's a plasma at a high pressure used to knock the metal atoms out of your targets. So that is a technique generally they'll use. You can just see here the biasing what we are doing here. So from that cathode and anode. So cathode generally is your substrate. Anode is your your substrate region. Okay, so in between that potential difference, so that will direct your atoms towards your substrates. Okay, so that is the concept of this sputtering technique, and there are many types are there. Let us discuss one by one. You just see here, this is sputtering thing. When you are applying the potential difference, then when the ions are coming, the argon atoms are coming, and it is ionizing, it is going and bombarding. You can just see here plasma near to your substrate region. So this is the target. So I think it is a copper or PAN target. This is a magnetron. Okay, so many people, they have a confusion what is a magnetron sputtering and what is a normal sputtering. So magnetron, putting one magnetic field at the bottom, it will direct that the ejected atom from your target material to reach the substrate region. So that is called magnetron sputtering. So when you have this cathode above here, as I put as an image, cathode above and putting your substrate down, then ejected atoms, obviously due to that the gravitational thing, it will come down. But many times it will be ulta. So recent technology, what they will do is, you see here in this GIF, then a source, the target material will be here, and the source as a substrate, it is over here. So we need to cross that gravitational thing to reach that layer, the ejected atoms to deposit as a layer onto the substrate. So that is what the magnetron is coming to the picture, where and all the ions are charged particles, put a magnetic thing, it will be defining this path of the beams, the layer, ejected atoms, it is depositing on the substrate. So magnetron means just a magnetic field to direct your ejected atoms. Okay, that's it. So how does it work? You just see here. So there is a two sputtering things are there. So by applying a power, what will happen? That ionized things, the plasma will flicker over here. So that ejected atom, it will go and deposit as a film. This is how that sputtering technique will work. And now maybe you can ask the doubts what is the DC magnetron sputtering, and what is RF, and what is the DC pulse. So what difficulty is there in the DC thing? DC magnetron sputtering means. So when you take that aluminum target or copper target or gold target to make the electrode on your substrate or your device, so over a period of time, what will happen means due to the contamination or due to the power be impinging onto the target region, so surface, it will create some it will oxidize. When it's getting oxidized, then means the ejection of the atom from the surface, it will be difficult. So DC magnetron sputtering alone, if you have, so very difficult to compensate this surface charging, charge potential on the surface. Okay, so then what the people they are doing, actually they introduce that RF sputtering. So with respect to the radio frequency thing, we are cleaning the surface, and we are doing. Of course, we are doing the pre-sputtering before your main device, but with the help of the shutter. So even then, this biasing, surface biasing, that it is not compensated. Then RF thing, it is alternative, complementary for a DC, and DC pulsed. So if you have a DC first thing, definitely it is a complementary for RF for the metal deposition. So then there with respect to the pulse, then we are removing that charge potential on the surface, and we are making that metal substrate as a metal on the surface, because ejections are happening only on the surface. Keep the point in your mind. Okay, so why we need RF, especially if you apart from the metals, if you want to go for the metal oxide, DC magnetron sputtering, it will not work, because -2 to -5 kV, it's a maximum thing we are applying as a potential in the DC. So RF, it is much needed for that dielectric materials. There the RF is coming to the pictures. Okay, so what I'm trying to tell, it is the best technique in the world for the uniformity, and maximum, nowadays the source, the target materials and all, what and all they are bringing, the source region, cathode region. So it is a bending type. So most probably, you might have seen the olden days sputtering technique. Vertical source will be there. So this is the cathode region, and your substrate will be there. So either you have RF biasing to clean your substrate when you are depositing, or RF rotation things will be there. Substrate rotation for the uniformity. Substrate heating is also will be there. Okay, so that is the olden days. It's a vertical cathode. Okay, so now what they are doing, it's a bending cathode. With the bending cathode thing, what and all you want to optimize, definitely you can. You just see the GAF, what I'm showing is a bending cathode. So with the help of this, I can cover this sputtering yield region. So how much region it is depositing, then I can able to make. You can just see the substrate is moving up and down. So whenever some material that tooling factor means that sputtering yield, it is happening more depending on the material, that height variations we have to do, of course. So then we can tilt this guy, then we can make that precise coating on your substrate regions. Okay. And co-sputtering is also there. Co-sputtering means general sputtering, once this cathode, there are 2 cathode, 3 cathodes are there, means one cathode deposition done, then next cathode they will turn on and they will do the deposition. That is normal sputtering. Co-sputtering means especially they are using it for that, this one, composite making. Okay, so for example, zinc oxide is there, titanium dioxide is there, 2 target material I'm keeping over here. I'm just applying a PIA, that RF potential into that thing. Then when I'm applying RF power, what will happen? Then ejection of zinc oxide and ejection of TiO2 will come together, and I will make a composite under the substrate called co-sputtering technique. Okay, so what is the bottom line means, depending on your application, choose the right techniques. Okay, so which means if you are spending some money to purchase some new equipments, so before you are going and buying the thing, so do some thorough analysis. So whether it will solve your purpose or not. Many times what they will do means they will buy thermal evaporation. So and it is not solving the purpose of dielectric. They cannot go for the sputtering. It is costly. Then what they will do means buy some electron beam assisted thing. So change your system. So if you don't want thermal evaporation so long not needed, put a electron beam which is coupled with it, because it's a kind of add-on they are doing in their equipment to make it live. Okay, so this is about that fabrication things. And it's a ocean. So what and all the fabrication technology is a completely it's a huge topic. So let me touch. Once you made the film, then what you have to do in the following minutes. Okay, so now what is the time? Then it is 10:30. Okay, so I will take up to 11:30. So maybe another 1 hour. Let us discuss. Many people you are fabricating, but you may not aware what characterization techniques used for that. Okay, so let us discuss in the following minutes. Okay, so I made something. So for example, PVD or CVD or solution processing, I deposited some things. I don't know for what application it is suitable. For example, I prepared the solution. I have a target of zinc oxide. So I deposited whether it is a zinc oxide or not. I want to check whether it is graphene or not. I want to check means there this testing techniques it's coming to the picture. So that testing technique, that technical word is characterizations. Okay, characterization means you're just testing it. You just see there are some many foot colors there. So everything it is made up of some materials. Okay, so this material property it is much needed to study before you are making it as a commercial purpose. Otherwise something you are making, so that is really hazardous or harmful to the human being. So it is not at all recommended actually. So what they will do, the industry all coming here, there are many industry as I told already, they are coming and enrolling with us. So one of the small application before starting I would like to share. Unilever, I think Hindustan Unilever. So they used to come with that hair sample. So means they are, I think, I don't know how many people you are aware about it. So they will they will sponsor your hair if you have a long hair, especially for women. So if you have a long hair and if you're willing to use their product and you want to give a feedbacks, definitely they will pay for it. Okay, so that thing is also there. So what that Unilever people they are doing means they are making the product of shampoo. So they want to make as a anti-dandruff and anti-hair fall. So they will give some product to some customers consumers, so that after that they are collecting the hair sample with the shampoo, they are bringing, they want to do some testing over here. Okay, so what they are trying to do, so what they did in the sense they decorated with some zinc oxide nanoparticles. So nanoparticle means it is that anti-hair fall, and nano rod synthesis they did and over to mixed with that shampoo, it is anti-dandruff. So anti-dandruff and anti-hair fall, so completely they are controlling with the nanomaterials. Okay, so they want to study and prove that shampoo containing some zinc oxide nanoparticles or zinc oxide nanorods. Of course, they need this techniques, characterization technique, to prove it is the nanomaterial or this is made by the stoichiometric ratio and all. Okay, so hope you know vanadium oxide and there are many materials are there. It is having some different oxidation states. So with respect to the different oxidation state, the material toxicity will be there. Okay, so without knowing that, if you are prepared something and it is ready for your product means the phase it decides whether it is a toxic or not. Okay, so there this importance of the techniques, characterization techniques coming to the picture. So material characterization is there, and mechanical characterization is there, optical characterization is there, and as well as electrical characterization is also there. So a very important thing, most probably material characterization means it contains a scanning electron microscope to see the particles dimension, and we can do some atomic contrast images, or we can get the composition analysis by using SEM with the assistance of some add-ons. Okay, so TM is a transmission electron microscope complementary for the thing, and XPS. So we have a slide actually. So XPS and SEM only I'm going to talk today. So those are the techniques are there. So electrical characterization, for example, if you want to see the mobility of the material, so one of that most of the people they are not touching this electrical characterization part. So kindly utilize the things, so because there are many places that people they have, because charge carrier mobility is also important wherever you go for any applications. So oxidation state and as well as carrier mobility, it is a matter for your device making. Okay, so keep the point in your mind. So let us quickly start. So characterization techniques. So creams and shampoo, as I told already, one of the example. So water contamination, obviously it is much need to be taken care nowadays because what and all the water it contains depending on the area. So if this water what we are drinking near to the industry factory region, then obviously there are contaminated water only we are having. So how much level the tedious things that totally dissolved salts, the values and other things and all there, then we need this assisted techniques we can do it. Soil contamination, because they will use many users, customers, they are bringing civil engineering people, so they want to make some new cement or new kind of sand, artificial sand they are bringing. They want to construct something that kind of thing and all. They will come here, they will check the property of the thing. Of course, water filters, it's having most probably you might have seen in your home. Sediment filter is there, carbon filter is there. Each and everything before making it as a product, it is tested and it is qualified, then only it is coming to the picture. Okay, so then it is coming to the markets. Okay, so there this characterization technique is relying, and this is a quick example semiconductors and metals and insulators. So that property checking is also important. For example, if you want to make some electrode for your material, so you are depositing zinc oxide as a top electrode means it will not work. Zinc oxide is a semiconductor. Okay, so we need a metal to collect your charge carriers. Okay, so metal optimization or something you are making. For example, semiconductor TIN and iron nitride. So many people what they will use iron nitride and titanium nitride as a top. Knowing the property of the semiconductor and insulator and metals. So 99% I can tell 100% we need the strong evidence to prove what material we have. Okay, so these techniques will be useful. So first technique it's a X-ray photoelectron spectroscopy. Many of you people aware, and some of people are not aware. Then I will cover the things. So it is surface chemistry analysis can be done by using this tool. It's a part of material characterization. Okay, so X-ray photoelectron spectroscopy, the name it seems it will tell like what is the principle behind it. It is a photon. X-ray means it's a photon, we know very well. Photon in electron which is ejecting from your material atom mode. The ejected photoelectrons carry your characteristics of your materials, which means what is the oxidation state, what is the composition of your material. So that can be tested by using this XPS. So XPS means it's X-ray photoelectron spectroscopy, photon in, electron out. The ejected electron gives the chemical state or valence state of your material, and it will give the composition of the materials. Okay, so the other name of XPS is electron spectroscopy for chemical analysis. And how much we can able to detect by using this equipment is 0.1 atomic percentage. It is a detection limit of XPS. So for example, if you have some material, you did some doping, so the concentration of the material is less than 1%. So I will compare in the next slide the complementary technique what all is available. So up to 0.1% the doping concentration you want to check, XPS is one of the alternative or complementary techniques. Okay, so how much you can detect actually? So that's what we discussed, and how much lowest element it can detect. So apart from hydrogen and helium, it will detect all the elements. So it will start from boron, lithium to uranium completely, from atomic number 3 to higher atomic number it can able to detect. And what it will give two information. One is that surface level composition analysis, another one is the surface level chemical state of the material, which means valence state or oxidation state. So what state it is at? 0 state means a metal state, we know it's a +4 state. Of titanium, whether it is there or not, that kind of identification we can get it from using this XPS. So next important thing, it's a non-destructive type, so it will not damage your sample whenever you are coming and giving the sample of a device or whatever. So after the measurement, then you can get the sample back. So it's a non-destructive type. It will not damage your sample. Okay, so as I told, it's a photon in, electron out. You might have heard somewhere. So it's a well-known phenomenon is called photoelectric effect. So photon coming and hitting and knocking out the electron from the material atom. So that is photoelectric effect. Okay, so what we are collecting here means anyway, when the photon with the energy coming and hitting, if you have atoms, so K shell, L shell, M shell, L shell and all. So K shell having 1s orbital and 2s orbital and 2p orbital, L shell having 2p, 3s, 3p and 3d, 4s and all. It is there over that orbitals. So whenever I'm just coming and hitting with some energy, knocking out the electron from that innermost level. So which means how much energy is required to knock out the electron from the innermost level. That energy we are calling it as a binding energy. So XPS deals with binding energy. So how much energy is required to knock out from the electron from the innermost level, core level. So that ejected electron is the binding energy. So each and every material having its own unique binding energy. So with respect to the corresponding binding energy, I can tell so what material is present on my material on the sample, and which is bonded with what. For example, silicon dioxide material you are bringing. So whether it is pure silicon is there or not, or silicon bonded with oxygen, or silicon bonded with carbon, anything. So with corresponding binding energy, it will tell us what is my material state. Okay, so that is how that XPS works. So what we are calculating here, it's a binding energy. How we are calculating the binding energy means H nu is the input energy what is coming and hitting, minus the energy which is going out having its own kinetic energy, minus the work function of the equipment. The equipment work function is there, it has to cross the barrier. Okay, so that energy minus will give binding energy. Some people they need a kinetic energy, no need to worry. Just like no kinetic energy this side, binding energy this side, that will give the answer. Okay, so this is how the XPS work. So let us discuss complementary technique. So you might have heard the composition techniques, surface level composition. This is surface level only, 10 nanometer. Why it is surface level and all we will discuss in detail in the following slides. So composition means stoichiometric of your materials. So for example, Fe2O3, if you're giving 2:3 ratio, whether it is there or not. Titanium dioxide 1:2 ratio is there or not. Zinc oxide you are bringing 1:1 ratio, atomic ratio is there or not. So that is called composition, chemical compositions. Okay. So you might have heard there are many techniques are available, characterization techniques are available to get the composition values. So the well-known thing is the EDS, energy dispersive spectroscopy detector. So it is add-on. Generally, we are doing add-on into the electron microscopes. So electron coming and hitting, and there are different electrons are knocking out from your material atom. So let me discuss quickly about the EDS and I'll come back to the XPS. Okay. So how does the EDS works? In the means, like, when you're applying the electron beam energy to knock out the electron from the K shell. So this K shell electron ejected, we are calling it as a second electron that is carrying that surface morphology of your image. So this is the K shell, this is L shell, means primary beam coming and hitting and knocking out this electron out. This ejected electron, we are calling it as a second electron. That is carrying the surface morphology of your image. So 99% if you are doing the SEM means you are collecting these second electrons only. Okay. So once this guy ejected out from the K shell, what will happen? That L shell will come and occupy the vacancy. Due to the ionization, what will happen? It will release in terms of photons. Due to that higher level to the lower level jumping, it will release energy. So that radiative energy, in terms of thermal energy, in terms of photon energy. So photon, we are calling it as a X-rays. So electron in, X-ray out, characteristic X-ray out, that is a concept of EDS. So don't confuse yourself. XPS is ulta. Photon in, electron out, that is XPS. EDS is electron in, X-ray out, it is EDS. Okay. So what it will give? Ultimately, what we are trying to do, we need to get the composition. So how does it matter for me, electron coming and hitting or X-ray coming and hitting? You can ask. Okay. So the bottom line, we are comparing these two techniques. It's a very useful techniques. With that, we are trying to convince ourselves which is more reliable. That is much important. Many techniques are available. Before you are giving the sample, you should know what you will get as output, how much is reliable and all we should know. Detection limit as well. Okay. So what I'm trying to tell, EDS is electron in, X-ray going out, depending on the energy level, it can reach K shell, and sometime it will reach L shell as well. The M to L transition will happen there. Okay. So what I'm trying to tell, when the transitions are happening from L to K, K alpha characteristics X-ray will come, K alpha, K beta, K gamma will come. Okay. So then due to this, this transition to this, then L alpha will be there. So K alpha, L alpha. So here we are dealing in terms of shell level in EDS analysis. Keep the point in your mind, this is the shell level emission only we are getting. So when this K alpha having its own energy, the corresponding energy, it will give what element is present on my sample. Okay. So you can just see here in the EDS spectrum. So this is, I think it is a WO3. So you can just see here there is some oxygen peak and W peak and all it is there. So in this, that area under the curve intensity ratio, it will give the stoichiometric of my material. So for example, you just see it is L alpha and this is K alpha, my tungsten. There are many things are there, K alpha, K beta, many things are there. Energy variations are there. And with respect to the highest intensity ratio between the W and the O, it will give the stoichiometric. Okay. So what I'm trying to tell here means we are dealing intensity versus energy in EDS analysis. Okay. So we are not dealing in terms of orbital level. Okay. But comparing to the XPS, we are getting 1s level orbital emission, 2s level, 2p level orbital emission we are getting. So orbital level emission, it will be much more accurate than the shell level emission what you are getting from the EDS analysis. That is the first point we have to think, which means XPS is little bit higher. Okay. Second thing, if you are coming with some material MOS2. So MOS2 means the molybdenum, some material for example, as I told KLM and all is there. So sulfur K alpha, it will overlap with the molybdenum L alpha. So both it will fall exactly on the same energy region. So when the molybdenum and sulfur falling on the same line, how do you know whether it is a molybdenum or sulfur? So it is very difficult to reveal the things. Okay. So that is one of the drawback of this EDS technique. So complementary for EDS is WDS, wavelength dispersive spectroscopy detector. So we used to call it as EPMA. So electron probe microanalysis, EPMA. I think you would have heard the word and you would have done some measurements as well. So when we are dealing in terms of energy with respect to that, we are getting the overlap in EDS and we have to go for the WDS. WDS we are dealing in terms of wavelength. Each and every energy, K alpha and K beta, K alpha 1, K alpha 2, K alpha 3, this energy, we are not able to differentiate in EDS, but in terms of wavelength, we can distinguish in WDS. So there, we can get the overlapping issues and all, it will be solved in WDS technique. Okay. So keep the point in your mind when you're giving the characterization, there is some energy overlap. Don't relay the EDS results simply. Okay. So generally, we will not agree, when you're, if I'm the reviewer, if you're putting the EDS results means, generally I will not accept. The reason, there are many drawbacks are there in this technique. EDS, how it will work, we seen K alpha emission, L alpha emission with respect to the beam, the transitions are happening fine. Okay, so apart from that, if I have some sample, for example, silicon dioxide, mostly it's a glass slide. So over the glass slide, you deposit it as a zinc oxide. Or why I'm telling zinc oxide means it's a universal metal oxide. Most probably 99, but still that zinc oxide research is going on. In future, I'm sure in future also definitely the zinc oxide people they will not leave because it is having n number of applications. That's what I'm just taking the common example as a zinc oxide. Okay, so glass slide is there and you deposited some 100 nanometer of zinc oxide over to the surface. So when you do the EDS analysis, what will happen? EDS concept is the penetration depth, it will be relying on two concepts. First concept is how much accelerating voltage you are applying with respect to the penetration depth, it will be there. Okay. Second thing, like atomic number of the materials. With respect to the atomic density, the penetration depth, it will be there. Okay. So whenever you are coming and doing the EDS analysis, keep these 2 points in your mind. One is accelerating voltage, how much you are applying. With respect to the penetration depth, it will be there. And atomic number is also matter. So lower the atomic number, higher penetration will be there even at lower accelerating voltage. Higher that atomic number, even higher the lower atomic number if you have, the penetration depth it will be less. So what I'm trying to tell, zinc oxide 100 nanometer, a glass slide is there. When you do the EDS analysis, you will get a peak for oxygen, you will get a peak for silicon, you will get the peak for zinc. So you can ask I'm interested only in the zinc and oxygen, where the silicon is coming. Silicon is coming from your substrate. So soda lime glass, sodium and many things it will be come into the picture. Dr. Rajesh sir, can I answer some of the questions? There will be some raised hands. Do we need to answer here it seems or sir? Hello? So anyone can unmute and tell whether can I answer it or can I move ahead and later on? Am I audible?
Yes, sir. Yes, sir.
Okay, so what can I do? You can give your suggestion then whether I can. Can I answer now and move on or at the end can I? Actually, sorry sir, your voice is breaking.
Sir, you can move on, sir.
Okay. Okay, fine. No worries. I will answer all your queries and before I'm leaving. So I will promise you. Okay.
Okay,
so no
sir.
worries. Okay.
Power cuts are.
Yes, sir. Parvala,
okay, continue. Okay.
Okay.
Sorry for
no issue. Okay. Okay. So what I'm trying to tell, where I stopped. Sorry. Okay. Okay. So zinc oxide and the silicon dioxide are your substrate. So silicon peak will come, oxygen peak will come, zinc peak also will come. So my question is how do you know the oxygen what you are getting, which belongs to your substrate or your top layer? So it is very difficult to answer it because the oxygen it is taking from your substrate and you are getting the intensity of the things. Okay. So one way we can play around if you have SEM in your hand, because 99% what you are doing, you are preparing something and you are dropping to someone who is doing that operating the equipment and we are getting as a results. But how do you ensure it that we are getting the good data? Okay. So that is what I'm telling, that accelerating voltage and atomic number is a play around. We can play around the things. Further, lowering the accelerating voltage. For example, 20 kV or 30 kV, they are applying for the maximum 30 kV only we can apply in SEM. So 20 kV, for example, you are applying as accelerating voltage means penetration depth, it will be a couple of microns. So 100 nanometer is your film. So you can control the accelerating voltage, especially it is coming only from the surface. That is one of the way you can enhance the signal from your top. Other way, what we have to do, we can tilt the stage vane angle. It is more exposure onto the sample surface. The penetration depth I am controlling only to the surface. That also can be done. Okay. So even that, you are getting, what we have to do means do a cross-sectional EDS analysis that is reliable. Okay. So when you're putting that sample vertically and you are looking 100 nanometer and you are making a point and you are getting the EDS analysis, that will be reliable, but conditions apply. So what is the difficulty we are facing means because glass slide is an insulator and the top layer is a semiconductor, zinc oxide is a semiconductor. When you do this thing, what will happen over a period of time, the beam exposure, that substrate because due to the charging effect, there will be some drift will be there in your position of your sample, because when I'm clicking over here, So first time like now it will be here, like now first second, third second, fourth second, and all due to the charging effect, it will go down. So what and all we are measuring, it is not from your sample, it is coming from somewhere outside only. So you may not get the results properly. So there charge compensation, gold coating and all it is coming. Then I will discuss more in detail in that following things. Okay, so what I'm trying to tell. So when you are doing this glass slide, thin films, glass slide is a substrate and oxide material you are depositing over the top of the thing. 99% you are making a mistake. That oxygen count 90% is coming from your substrate only. 10% only your material stoichiometric ratio. So keep the point in your mind. So that is one of the drawback of EDS. Second thing is if your sample is non-conducting materials or it is a semi-conducting material. So the condition for the electron microscopy is it should be electronic conducting. So if your sample is a semiconductor insulating, how I can make electronic conducting means, so they are artificially we are sputtering the gold, what we discussed there in the sputtering technique, same concept here, the portable sputterings are there to make the surfaces conducting. What generally we are doing, so this is your substrate, this is your top layer means, so for example, this is your layer, this is your substrate means. So from the sample surface to the holder, the SEM holder, so we are just sputtering and we are creating the grounding part. So the sputtering gold coating is nothing but creating a grounding part. So when you create a grounding path, whenever the beam is coming, if it is a metal, then electron ejected, actually it is finding a grounding path, it is grounded. Excess of electrons are grounded. When it is a metal oxide or if it is an insulator or whatever thing you are bringing, so when the beam is coming, it is not finding any grounding path, it will accumulate the charges on the surface. This charge accumulation only we are calling it as a charging effect. So how to balance the charging effect? Artificially, we are creating the gold coating from the sample surface to the holder, we are creating the grounding and then we are doing the analysis, it will not charge much. That's one other thing most probably you know very well. Okay, gold coating generally we are doing. But keep the point in your mind, it is not always mandatory you have to do the gold coating. For example, sometimes our people also making mistakes. So metal, they will come and they will do gold coating. It's a default, it's a mindset. Default, they will deposit and they will put it in the SEM chamber. Not required. Metal, why we need a gold coating? Okay, semiconductor insulator, we have to do it for charge balancing. So think if you want your sample back. So for example, your sample, it's a device. You made some devices over the glass slide, or some silicon or whatever thing you made. So material is a metal oxide on the surface. So when I'm giving the sample, I want the device back for some other characterization I'm doing. So what we have to do generally, you will not do any gold coating. When you do the gold coating, you have to discard the sample. It is not useful so long. So in that case, gold coating is ruled out. We can control with the accelerating voltage what you are doing, working distance and current how much you are applying. There are parameters are there you can play around. That's what I want to tell. Second thing, even that you are not getting, ground the sample by putting some copper tape or carbon tape or silver paint and all. 4 corner. If your sample is that square sample, put all the corner silver paint or carbon tape or whatever. So then it is balanced. Whenever you are going to the particular region, the charge balancing is there, you can get some clear images. So conditions apply. When you want your sample back, gold coating, it is not a right way. So even that it is a PDMS is my substrate or highly polymer substrate I'm bringing, it is highly insulated. Middle portion also alumina deposited, actually it is, that is also highly insulated. So what I have to do, which means one sample, there is no other option, we have to sacrifice, finish all your characterization, come back and do SEM with the gold coating. Okay, so that is the only way we have. Okay, so what I'm trying to tell, EDS, why it is not much reliable means, if you're coming with a non-conducting material, zinc oxide or insulating sample over the substrate, doing the gold coating, you're doing the gold coating. So by mistake sample fallen down, you just fallen down and you're taking, and people are not saying, then you're putting a desiccator and you're handing to the operator, they will do inside that EDS analysis. Unwanted peaks it will come. So gold peak will be there. We know very well it is what we deposited. Carbon, oxygen, nitrogen is a contamination, you know very well. So hydrogen we cannot detect, ruled out. Okay, so there are some unwanted peaks are coming means, so generally what the people if you are people coming and sitting in front of us and you are asking you want only zinc oxide means, remaining all the things we are omitting. EDS having the option to omit, the software having the option to omit these unwanted elements. You want to add something, you can add. So as a person reviewer, we know very well. So we can do many simulation kind of things in EDS analysis. That is what it is not reliable, because you can tell the percentage in the tabular column, but you cannot hide the peak position in the EDS analysis. Okay, so keep the point in your mind. I should not tell many things because people, they will catch and they will focus only on that malfunctioning their data. So we know the loophole. That's what I'm telling. We can do many things. So none of the technique is reliable. So that's a point I want to share. Even XPS also. You can do many Chinese people. I don't want to comment, but Chinese people, they will do a lot of manipulation in their data. So of course, some of the Indians also comparatively equal. So what I'm trying to tell, we should produce some results which will be reliable. So for example, I want to quote the small point. If you are writing your paper with a mistake, it published, tomorrow it will be literature for the upcoming people. Keep the point in your mind. Write it as it is. If it is not coming, no problem. So just you do something, you try to get it actually. That is what I want to tell from my side. So if you're writing today with the mistakes and definitely, for example, you omitted nitrogen, you omitted gold or whatever things which is coming. Newly starting the thing, then it will direct into the wrong way and they may not get the results. After not getting the result, then they cannot go anywhere. So we are misleading the people who they are upcoming. Okay, so fine. So I don't want to involve into the things, but just what I'm trying to tell, the EDS, it's a complementary for XPS, but we are dealing in terms of energy over here. And there are drawbacks are there. Energy overlapping is an issue. And so then next thing is that penetration depth concept is also there. And if your sample contaminated and if your sample containing gold, you can only omit the percentage in the tabular column. I think you might have seen the EDS data, the tabular column, they will give how much weight percentage, atomic percentage and all. You cannot omit this spectrum position in the EDS. So if I am the reviewer, I will ask instead of the tabular column, put this EDS spectrum. So from there, I know the intensity ratio, how much is there. Even if you are manipulated also, then I can catch immediately. Okay, fine. So ruled out. So next I'm coming back to the XPS. It's a complementary, as I told, WDS, EDS is there, atomic absorption is there, many things are there. XPS stand for it is, we are dealing in terms of orbital. So that is why it is much more accurate than any other thing. And binding energy, it's having its unique binding energy. Of course, here also the energy overlapping issues are there. So because some material core level, it will overlap with some other material outermost level. So that energy overlapping, it may confuse you. Okay, so that we will discuss in detail quickly in the following slides. So what I'm trying to tell, XPS and EDS, both are there. You choose which technique it is useful for you. As I told, EDS, XPS, we can detect up to 0.1 atomic percentage. But what about EDS? How much I can able to detect now? So I can detect only 1%. So less than 1% identification, don't go for EDS. It is not reliable. Second thing, less than sodium, don't conclude your composition by using this EDS analysis. So less than sodium, not preferred. Less than 1 atomic percentage, it is not reliable. So XPS scores for 1.1 atomic percentage, and EDS it will detect from boron to uranium. So lithium and beryllium and all, it is not possible in EDS. So then we have to go for XPS, because lithium is, for example, you are making some lithium doping, or you are making lithium batteries. So that case, definitely EDS, it is not possible to detect because of the detection limit. So XPS is the only tool it can detect from lithium. Okay, so that is the comparison between these two complementary techniques. So first application part we discussed, and second thing, now we are in that surface level oxidation state or chemical state. So chemical state means which is bonded with what? So carbon, it is there, carbon-carbon bonding and carbon-oxygen bonding, carbon-nitrogen bonding, carbon-silicon bonding. So corresponding the binding energy position, it will tell the functional group of the materials. Okay, that is what I'm trying to tell, that chemical state or functional group of the material. Oxidation means whether it is a 0 state or +1 state or +2 state. That is much needed for your electronic mobility, or any application you go, this oxidation state is important. Material property define this oxidation state. Okay. Okay, so what is how we can compare with the other techniques? So phase identification. So for example, if you are coming with that copper oxide, so Cu2O and CuO, or zinc oxide you are bringing. So I want to prove zinc oxide, what I deposited, it is in the pure crystal state, or pure state of my material. So what and all the complementary techniques are there means, XRD is a well-known technique, X-ray diffractometer. So there X-ray signals are coming and hitting, then diffraction things are there, and with respect to that 2 theta value, the corresponding 2 theta position, with respect to the literature survey, JCPDS file, and we are matching and we are telling it is zinc oxide one way. Second thing, like, what is the use of XRD? We know very well. It is a orientation identification we can get. So if you're coming with that, like, highly oriented material, polycrystal material, so corresponding, like, orientation position you will get in XRD. So zinc oxide, if you bring, of course, XRD is one of the complementary techniques. Second thing is a Raman. So it's a phase identification sample only. So when analysis only. So if you have a zinc oxide and you're doing the Raman is a vibrational spectroscopy. Hopefully you know well, like Rayleigh scattering and Stokes and anti-Stokes and all, it is there. So it's a scattering phenomenon. Whenever you're coming and keeping your sample with respect to that excitation wavelength what you are applying, there are different wavelengths are there. So of course we are using a laser over there for Raman. So UV region to the IR region with respect to the material nature, and we are doing this vibration study. So just it is the vibrational state of your material in Raman. Okay, so there if you do that zinc oxide, I will get a Raman shift peak, corresponding Raman shift peak, then I can tell this material is present. Complementary for Raman is FTIR. So Fourier transform IR spectroscopy, it's absorption phenomena. So for example, if I'm the molecule, when I'm just shining the IR light, so if something I absorb, then I will get the inverse peak. It will be collected in the detector which I'm keeping in the backside. So IR source coming and hitting the molecule where and all it is absorbed, then it will be collected there. So this absorption phenomena, it is a concept of FTIR. So XRD is a diffraction phenomena, Raman is a scattering phenomena, FTIR is absorption phenomena. These are the complementary technique to find out the functional group of your material. If I'm coming with a graphene oxide and so Raman, I can get XRD, something I will get, and FTIR also I can do it, I can finish my work. So why we need to go for XPS analysis? Generally, you will ask. Okay, many people they will ask. So why you need to worry? Because XRD means a 2 sample we can do it in 1 hour, or depending on the conditions. Where the here in our center, my internet it is showing unstable. So is my voice breaking? Friends?
No, sir. No, sir. Continue. No, sir.
Okay, fine. So I got a message. It's showing some internet. It's a bit slow.
Sir, I think PPT is not visible.
Okay.
PPT is not moving, sir. Can you explain the XPS is used to bind?
PPT is not moving. Oh
Yeah.
my God. No. I'm just still in the same. No. I'm in the same slide only. I'm explaining
Okay,
that
okay,
complementary techniques.
okay.
PPT I'm not moving because this is a slide I want to compare. Yeah.
Okay, thank you.
Okay, sir. Sorry. Oh, my friends also there, I think, Professor. Okay, I can see my many friends here. So good. Okay, so what I'm trying to tell, so XRD, Raman, FTIR, those are the complementary techniques we have. Yeah. So why we need to go for XPS? So we need to think in our before we are doing, we have to. So what I'm trying to tell, XRD 2 samples, generally we can do it in an hour. Many people, many places, they are doing 4 sample, 5 sample in an hour. So Raman, we can do some 5 to 6 sample minimum in 1 hour. FTIR, it's a quick process. Within 1 hour, you can complete 10 samples. I'm sure. Okay. So XPS is a time-consuming process. So it takes nearly 1 hour or 1.5 hours. Each element scan. If you have a zinc on the oxygen means zinc alone, it will take 20 minutes. Oxygen alone, it will take 20 minutes, 30 minutes like that. So it's a time-consuming process. Why we need to waste our money and why we need to waste our time? It's a it's a kind of expensive technique like TEM only. XPS. Okay. So what is the drawback of those techniques? XRD, Raman, and FTIR. Drawback of the XRD, if you're coming with amorphous samples, so definitely we cannot get the phase identification of the material. So many times, whenever the people are coming, they want to go for amorphous based application. Means if I want to find out, XRD is ruled out, Raman and FTIR, you will get a broad spectrum. You may not get any corresponding the phase identification using these 3 complementary techniques. Okay. So amorphous based materials, it's a drawback. There the XPS is coming to the picture. XPS does not matter, it is like a crystalline amorphous. What we are collecting in generally, it is the binding energy of your material. So corresponding binding energy, you can tell what is the state of the materials. So this is the first application advantage of XPS. Okay, then these 3. Second thing is metal based material. For example, if I'm coming with the metals, as I already explained XRD, definitely you will get the metal samples diffraction. Perfectly fine, but whatever Raman and FTIR, as I told, it is a scattering phenomena. Metal means it will reflect more. FTIR means if I'm keeping here, instead of absorbing, it will reflect it back. So in that aspect, metal based identification, metal bonded with metal, metal bonded with ligands, metal bonded with any other thing. So these techniques are little bit difficult to get the information of the metal based samples. XRD. So what I'm trying to tell, like when you're doping something, metal doping you're doing with the zinc oxide, for example. So then over a period of time, what will happen? Either the intensity of the peak, it will vary in XRD, you might have observed it. And second thing, like there will be some offset will be the position. So that is an indication something like it is going and occupying this atomic space, that impurity, whatever we are doing, it is placing into that. Okay, so that is the evidence intensity variation and shift in that peak. So keep the point in your mind, there is some difference between the doping and composite. So over a period of time, 10% beyond your doping, so that is not called as a doping. So it's a composite. Okay, so that kind of identification, XRD, obviously intensity variation, peak shift variation, we can get it. But it's a very, very difficult to conclude the material, the metal, what and all you are doping, it is there on your material. So we have to do some refill analysis, and it's a refill refinement we have to do. It's a time consuming, and it's a more accurate way, of course, completely agree. So easily quickly want to check instead of going with the XRD thing. It's a complementary, just confirmation. We can do it with the XPS as well. That's what I want to convey in this slide. Okay, so the summary of this slide, XPS can be used for two applications, which we discussed. Keep the point in your mind. One is the surface level composition analysis, surface level oxidation state we can get. So XPS we are dealing in terms of binding energy. That is what it is much more accurate than that shell level emission what we are happening in EDS analysis. At the same time, detection limit, it will start from one atomic percentage in EDS, and boron to uranium is reduction limit in EDS, and lithium to uranium, it is a detection limit in XPS. 1.2 atomic percent can able to detect. So what I want to tell here, if your doping concentration in the ppm level 0.1% less than that, both the techniques are ruled out. We have to go for that liquid chromatography technique, or SIMS secondary, if it is film or something, then SIMS secondary ion mass spectroscopy is one of the complementary techniques available to detect your doping in terms of ppm level. That's the bottom line. Okay, so quickly I will go through what I have. So typical XPS data, how it looks. So XPS data look like this. So 1200 EV to 0 EV, we are scanning on your sample. So when you scan, what will happen, where and all the orbitals are there, corresponding peak position you will get. The corresponding peak position tells what is that elements, what and all elements are present, and what and all orbitals are there in your material. Okay, so quick explanation about the X-ray source. Not all the X-ray source suitable for XPS analysis. There are some conditions apply. The energy should be high as much as possible. That is the first criteria. So then only we can reach always to the K shell, and we can knock out that 1s orbital. Keep the point in your mind. But at the same time, the second point, full width of maximum. That is the line width of the source. Energy source broadening. So that will happen when you are increasing the energy, keep on increasing the energy. For example, carbon 1s. Carbon is my material. So K shell 1s is always core. Keep the point in your mind. So 1s orbital, if I want to knock out in the carbon material, 284.6 eV, it is the binding energy of carbon 1s. So that much energy I need to knock out this guy out. So what and all I'm applying, for example, 1000 EV, if I'm applying as energy, 284.6 EV, it will easily knock out. So no need to worry about it. For example, little bit higher atomic number, if I'm coming zinc L shell 2p orbital level, it seems it required 1010 EV. So 1000 EV when I'm applying as input energy, it will not reach to that little bit outer shell as well. Okay, so then if I'm keeping some 1500 EV or 2000 EV, so it can reach to that like a 2p orbital of zinc, but 1s orbital of zinc, if I want to reach, I need some more than, for example, I need some more than 5000 or 6000 EV. So which is not possible with respect to the input energy. So similarly, if I'm coming with the higher atomic number, Ag, platinum and all, so I cannot reach to the core level always. So that is what, as I told, the energy should be high as much as possible to reach and knock out the electron from the innermost level. But at the same time, if I'm increasing the energy, keep on. So full width of maximum, the line width of the source is also keep on broadening it. So when it is broadening, why you need to worry? Because I'm reaching the core, like that you can ask. But when I'm broadening a thing, whenever you are coming with the functional group material or nearby bonding information you want to get, carbon, oxygen, carbon, it will be very, very close. If you want to get the good resolution, that line width should be as much as possible. That's the bottom line. Okay. So energy and FWHM, we have to balance both. In that aspect, aluminum and magnesium is play a crucial role. And the energy of aluminum K alpha is 1486.6 and the magnesium K alpha is 1253.6 eV. Okay. So source is constant now. What can be varied in the sense that orbital level only it can be varied. So because universal source we are used to call as a universal source, aluminum K alpha and like magnesium K alpha. So 1486 eV as an input energy is constant now. Carbon means 1s orbital I can easily knock out. Zinc means 1s I cannot reach, 2p level only I can reach. So zinc 2p is my core level with respect to the source energy of aluminum K alpha. Then little bit of higher atomic number, Ag3D means a 368.2 eV, that is a binding energy of Ag. And if I want to go to that Ag2p and Ag1s means I need some huge energy. That is not possible because my input energy is constant. So depending, the bottom line is depending on the energy, I am choosing my the core of my that higher atomic number to the lower atomic number. That's the bottom line. Okay, so that is what whenever you are reading your paper, you might have seen that zinc 2p, titanium 2p, tin 3d, platinum 4f, something and all they will mention. The reason 1s is always core, but at the same time the energy input energy, it is not sufficient to knock out the electron from the 1s level, so that I can reach only to that valence level or outermost level only. That's the bottom line. So many people, they have XPS, they may not have the monochromatic source because the cost of the equipment what we have in our center, it is 8 crore. So 4 crore we are spending only for the monochromator. The reason you can just see there are a lot of background. So same concept applicated, it's a secondary electron emission only. XRD, I think you might have seen any spectroscopy you take, the secondary electron emissions will be there. That second electrons it will produce a background. So if you want to avoid, of course, we need a monochromatic source. So this monochromatic source, it will avoid the background. At the same time, it will avoid that unwanted satellite peaks. When you see here, there are some small hump because of that, different wavelength coming and hitting on your sample you will get, and huge background rise is there. So it's very difficult to interpret your data. So monochromatic, it is important. So next thing is the why XPS is surface analysis. Of course, XPS, how much X-ray can penetrate, you know very well. X-ray can penetrate into a couple of microns. There is no doubt about it. But this technique is surface chemistry analysis. The reason is the photoelectron which is coming from your specimen out, it is very, very weak. So which means kinetic energy is very high means binding energy is very less. Binding energy is very high means kinetic energy is very less. So most of the higher atomic number when you are going away, higher atomic number, then higher binding energies are there. So kinetic energy will be very, very weak. So escaping depth, it will be very less. So D is equal to 3 lambda. That's a formula we are using. Depth, how much we can get. So typically 35% of the photoelectrons can be harvested. So 3 times the lambda. Lambda is an inelastic free path. This electron which should not collide with anything, it should escape from your material. So this inelastic free path concept, it is playing a crucial role. So its conditions apply. All the materials not coming from the same depth. As I told, the conditions apply for EDS, accelerating voltage, and atomic number that decide the penetration depth here as well. Okay, so how much I can harvest the photoelectrons of any material means 2 nanometer to 10 nanometer, it is a maximum. So which means 3 nanometer, it is a 3.3 nanometer is the maximum depth of 1 lambda. So 1 lambda is 3.3 means D is equal to 3 lambda, 3 into 3.3, maximum 10 nanometer only we can harvest by using XPS analysis. Okay, wherever you go, this concept is applicable. How I can enhance that, increase the penetration depth means either I have to increase the energy. So I have to vary some other concept, tilting by stage one angle or something I have to do. So when I'm increasing the energy, what I have to criticize that what I have to sacrifice the thing means full width of maximum, it will be broadening. If the energy is high to get the penetration depth more and more. So at the same time, line width is keep on increasing. So in that concept only that people they're using this XPS. Okay, so what data contains? XPS containing 2 informations. One is that white spectrum, another one is that higher resolution spectrum. So white is nothing but a survey scan. EV to 0 EV, we are completely scanning on your sample. Where and all orbitals are there, you will get a peak. That is the first advantage. Second thing, we can identify the core and as well as at what and all other orbitals are there. Third thing, what and all the impurities are there in your material you can. And at the same time, there are some Auger electron peaks. So what is the Auger electron peaks in the sense? It's a 1 electron or photon, whatever the energy coming and hitting, 2 electron concept. So Auger electron quickly I will tell you, when the beam which is coming and hitting your K shell, this ejected electron, we are calling it as a secondary electrons, perfectly fine, we know very well. So this electron only, photoelectrons only, we are collecting, fine. So this vacancy will be occupied by the L2K. So once it is occupied, I think it will release in terms of photons. These photons, while going out, knocking out the nearby shell electron, that ejected electron we are calling as Auger electrons. Okay. So sometimes this Auger electron peaks also will be there in your spectrum. So we need to index your data. What I'm trying to tell, XPS is a spectroscopic analysis. You will get something. We need to interpret each and every line corresponding to what. Okay, so that's a bottom line. So whenever you're indexing the thing, some of the thing, for example, you see here this example. So some regions are like not able to index, it is not matching with anything. Immediately you have to check your literature or some database. Where is your other electron of your main material? That's a bottom line. Okay, so once this wide spectrum done, so from that, as I told, the first application, composition analysis can be done by using this wide spectrum only, which means the area under the curve, intensity ratio. For example, this is zinc and oxygen, means this intensity ratio, which will give the composition of your materials. It's a universal constant. So you know intensity ratio only, composition generally we are getting. Okay. Second thing what we are getting means narrow scan or high resolution scan of your materials. So zinc and oxygen is there. This my sample is the zinc oxide in the sense. Particularly, I'm taking the zinc, this region, and oxygen, this region. Doing the slow scan is called high resolution or narrow scan. So the resolution, energy resolution will be much lower than what you're doing in the wide scan. So what we are getting in that, the high resolution scan means there, you will get the corresponding binding energy portion tells which is bonded with what. For example, silicon bonding means it will be there in the 99.2 eV or 7 eV. When the silicon is bonded with oxygen, this peak portion, it will not be there, it will be shifted 103 eV. So when the silicon bonded oxygen peak at 103 eV, silicon bonding is 99.7 eV. That position tells what is the my material state. Okay. So then this is the zinc, and slowly I'm doing it for next thing I'm doing it for oxygen. So corresponding portion, as I told, then we can tell which is bonded with what. So you just see here, there is a higher intense over bonding, and this is a small intense peak. This is corresponding to zinc and oxygen bond. Okay. So this is how the typical XPS data looks. Okay. So now the question is how do you know the data is correct? So with that, I will quickly skip because it's already running out of time. I don't want to waste your time as well. So dumping all the thing on the same day, I completely agree. So if I'm the audience, then I will feel the same. So I'm extremely apologies for that. But these are the techniques before you are going, you should know about it. That is the ultimate intention of this technical meeting. So completely there are many techniques are there. Whenever we have some time, then definitely we will discuss about it. Just it's as a beginning. So let us do many technical meetings. So kindly involve me also as well. Then let us do some technical activity. Then so this is the knowledge sharing. So what and all we know, then we are sharing. So many of the things we are also not doing. So when you conduct this kind of thing, then it's a kind of mutual sharing actually. So I want to participate hereafter the technical meeting, what and all is going to happen in future. Okay. So quickly, I will take some 10 more minutes. Sir, can we take 10 more minutes? Is it fine?
Take it, sir. No problem.
Okay, sir. Thank you so much, sir. Okay. So the question what I asked, you are giving some sample, zinc oxide or whatever you given. I did a wide spectrum for you, and I did a high resolution spectrum for you. How do you know the data is correct? Okay, so it's a common question generally you will ask. Not only this, any spectroscopy technique. For example, Raman spectroscopy you are doing. How do you know the data is correct? How many people to be frank, you tell me, how do you know that the equipment is calibrated? It's a tricky question, but we should ask. When you are paying for your slot, you have all the rights to ask. Okay, so Raman, what you're doing, we have a silicon standard 550 or 520.5 centimeter inverse. That is a big question for silicon, and how much deviation is there. Then we are calibrating and we are doing it. So 99% the people they are not following it. Apart from some places, they are not having a standard to calibrate. What we are doing for XRD data, all are correct. No, it's not correct always. We need a standard silica. Put a silica and check the peak position of silica. When the silica is silica, then there is no offset in your position. Then the what and all you're doing on your sample, it is correct data. Similarly for FTR as well. So what I'm trying to tell for XPS, it's a spectroscopy. We need a reference line. So whatever we are doing any spectroscopy, we need a reference. That's the bottom line. So what reference work for XPS, which means that reference is a carbon. Okay. So you just see this is a wide and high resolution and all that we are giving. Fine. So we need a reference called carbon. So adventitious carbon. We are calling it as adventitious carbon. We don't know where it is coming from, but it is helping us to do some mean portion variations. So what is the concept mean? For example, zinc oxide, I'm depositing on the glass slide. Oops. Okay. So zinc oxide is my layer. I'm depositing onto the glass slide. Zinc oxide is the thing I deposit onto the silicon. Zinc oxide I given it as a powder. So for me, all as a zinc oxide only. But when I'm going and doing the analysis on your sample, the peak shift, the position variations are there. So we should understand why there is some peak shift. Okay, so you can ask like that, as I now, as I told, the standard reference is needed. So what generally calibration standard we are using in XPS means it is AG, silver metal only we are using it. So the silver metal, we are taking and we are keeping before your sample. I'm checking the AG portion. AG is perfectly fine. There is no offset in the AG mean portion. But when I'm coming to your sample, there is some shift. As I told, example, zinc oxide deposit on the glass slate, zinc oxide deposit on the silicon, zinc oxide as a powder. Different shift portion I'm getting. So what is the reason we need to understand? So the same concept what we discussed in SEM, the charge cloud. Whatever it is coming and hitting, forget about it. What is coming out is an electron. These electrons are not finding any grounding path. Of course, the charge accumulation, it will drift your peaks, actually peak portions. Okay, so we need to know how much deviated from the mean value. So what do we have to do? So I checked the AG silver when before I'm doing my sample. I went and checked actually AG is perfectly AG, but when I'm coming to your zinc oxide sample, it is having some huge variation. So the bottom line in XPS is the reference should not be in the side. The reference should be on the sample surface. So whatever the sample I'm going, I'm just checking that with some reference. Then only what and all I'm doing, it is correct. So what reference it can be? It can be carbon. So carbon is an element we cannot omit. Even if you go to space, also carbon will be there. So when you are exposing the sample in atmosphere, carbon coating will be there. And when you are keeping in a desiccator, carbon layer will be there. And when you are keeping inside that ultra high vacuum, it is made by stainless steel chamber. So the chamber containing small percentage of carbon that will degas. The degassed carbon, it will be spreading on your sample surface. So that we cannot avoid. So this contaminated carbon, it is helping us to do the shift correction. That's the bottom line. So before I'm going and checking the zinc and oxygen, how much is the peak portion, I'm checking the carbon portion, how much it is. So 284.6 is a CC bonding. So 284.6, instead of that on my sample surface, how much this guy got deviated. This deviation, that much shift correction I have to do for my remaining elements. Then only the data what we are doing in XPS, it is accurate. Otherwise it is junk data only. But 99% it is it's a hidden secret. They will not reveal when they are writing the paper. That's what I'm just insisting so many times. So whenever you are writing a paper, so kindly you just mention what what reference you taken, how much it is shifted from the mean value, this much shift correction you done for your remaining elements, and you got the peak portion. This is the actual accurate oxidation state of the material, like that you can write it. Okay, so the bottom line, XPS reference should not be side, it should be on the sample surface to do the correction. And what material it can be, what element it can be carbon. So it's a wonderful question you can ask, if a material containing carbon, what I have to do. For example, it's a polymer substrate or polymer sample, carbon, organic materials I'm bringing, graphene oxide sample. Obviously, the carbon peak portion will shift without knowing that exactly you are matching with the mean value, you're matching with the standard. So that is also wrong. Okay, so if a material containing carbonaceous elements, you cannot take carbon as a reference. We to take noble metal as a reference. How to take? If your sample, this is your sample, and graphene or something you drop casted. So one of the corner of your sample, you deposit noble metal gold. So before you are going to this region, you check where is the noble metal portion is, how much this noble metal of gold or whatever you are depositing. So that gold, it is 84.2, it is a 4F level of gold. So from the mean position of the gold, how much it is deviated, that much shift correction you can do it on your main materials, carbon materials. Okay, so this is much more important, because many people, what they will do, so they will search the literature. I'm not blaming them, but I'm telling that whenever you are paying for your any characterization technique, or even you are putting from your packet or you're using your project, we have to utilize it properly. That's what I'm trying to tell. So it is not literature they told and I have to do. So many people, what they will do means they will do Raman, they will do XRD, they will do XPS, they will prove zinc oxide is a zinc oxide. So ultimately what you're trying to prove, if you're writing and putting all the data in your paper, if I'm the reviewer, I will ask actually, so what you're trying to prove finally, zinc oxide is a zinc oxide only. So it's a waste of time. So Raman interpretation, XRD interpretation and all. Okay. So XPS is one of the really higher end equipment to conclude your results. Okay. So when you are make it as the main data, put the XRD and Raman. I'm not blaming then XRD and Raman. With the XRD is a fingerprint, Raman and XRD is a wonderful equipment. But at the same time, when you are trying to put all the data in one paper manuscript, so I don't prefer actually trying to prove what. So if we are interlinking and you are trying to prove some evidence, perfectly fine. If it is a new material, it's a well-known material, don't waste your time and don't put everything in your main manuscript. Put it somewhere in the supplementary if needed. Okay, so that's the bottom line. Next thing is the charge neutralizer. Of course, if your sample is a non-conducting material, and when you are doing the XPS analysis, as I told, the charge balancing, it will charge cloud, it will deviate your peak position. How to balance that charging effect here? I cannot do a gold coating, what we are doing for SEM. When you do the gold coating on your sample surface to balance the charging effect, so instead of getting your main material, I will get only the gold, because XPS is a surface chemistry analysis. Okay, so without gold coating, what we have to do means we have a flood gun, charge neutralizer gun. So just showering the electron from the sample surface to the holder, I'm creating the grounding path. So then I'm doing the analysis. So it's called flood analysis, flood gun analysis, or charge neutralizer thing. So there are many things are there. What we discussed so far, it is a normal XPS analysis. There are depth profiling is there. Depth profiling means each and every layer I can etch out by using argon ions, and I can reach out to the next layer. I can get the analysis called depth profiling. Condition supply. Normal XPS is a non-destructive type. Depth profiling is a destructive type. It will damage your it will damage your sample is one thing, fine, but it will change your oxidation state. So we have a case study, copper oxide. So the person who came with the sample is a copper Cu2O. And when we are doing the analysis initially, so the copper, it was in +2 state. When you are doing etching, it went to +1 state. Further we etched, it went to the metal state. So we can do whatever we want. So that is not ultimate aim, but at the same time, depth profiling, it will not solve most of the problems. Okay, there are many case studies are there and many literatures are available. It will change your oxidation state. Once it is changing oxidation state, there is no point of doing this XPS analysis. Okay, so depth profiling having advantage in each and every layer etching. There are now advanced depth profiling techniques are available. What we are using, it's argon. There are some carbon cluster based etchings are available. So that it will not change your oxidation state. So that is what depth profiling the people still there using it. Angle resolved XPS, it's nothing but thin film sample. If you are coming with ultra thin film sample less than 10 nanometer thickness, as I told, XPS 10 nanometer depth information you will get. Till the stage band angle, you can get more exposure onto the 2D materials. When you are coming with the 2D material, sheets materials, so graphene 1:2 whatever thing, we are preferred to go with the angle as well. Imaging can be done. XPS imaging is elemental mapping. Of course, it's a elemental mapping, but at the same time, it is not complementary for EDS mapping what you are doing in TM and SEM. So huge region. XPS is not. I forgot to tell you, XPS it is not a localized analysis. So because, for example, if you are coming with 1 centimeter cross 1 centimeter, so 2 mm cross 2 mm region, the beam is falling. The collection angle, it is 300 cross 700 micron, general aperture what we are using. Least aperture size what we have to collect your signal, it is 15 micron, which means that is your lateral resolution of your sample. So 15 micron is a lateral spatial resolution of your XPS analysis. Spatial resolution is 15 micron. So if you are coming with the carbon nanotube decorated with some nanoparticle, I want to localize, I want to get the analysis. Of course, XPS is ruled out. You cannot use. Go with that SEM EDS or TM EDS mapping, which is much reliable. Okay. So next wonderful thing is a UPS. So especially semiconducting people. So there is no time actually. So I'm just completing it now. So UPS, it's a ultraviolet photoelectron spectroscopy to find out your valence band maximum, which is the distance between the valence band to that Fermi level, and work function we can get it Fermi level to the vacuum level. That work function also we can get it, especially who they are working on the semiconducting field. So UPS is one of the best technique to find that band elements. Okay, so band energy, where it is there, and we can make a steps whether the electron transport will happen or not, or hole transport will happen or not, we can determine. Okay, so this is the things which I told, and I just keep. So quickly, I will just show you the scanning electron microscope. So why we need a scanning electron microscope? Quickly, I will tell you. Human resolution, we know it's a 15 micron is the maximum we can. Of course, we need an optical microscope to go below that. So ultimate advanced optical microscope can go up to 0.4 micron. That is ultimate resolution. So 0.2 is the maximum thing. Below that, so below 0.2 micron or 200 nanometer thing, we need a tool called some electron microscope. We know very well. Electron microscope, two types are there. One is SEM, another one is a TEM. So when we have to use SEM, when you have to do TEM, with that I will complete this session. SEM, whenever you want to see the surface morphology of your sample, the resolution you want to get up to 10 nanometer, it is reliable. You can get something. So normal SEM and FESM, there are differences are there. They are using the normal tungsten filament. The resolution is 50 nanometer only. FESM means the people, they will use sharp tip, 100 nanometer sharp tip. The resolution of the guy, it can go up to 0.8 nanometer. So choose the equipment correctly. Whenever I have some sample, SEM and FESM. SEM means don't waste your money. Directly, if your FESMs are available, go there. Or my sample is I'm doing large grain boundaries. I don't want to waste my money in FESM. Choose SEM. Ultimate resolution is 50 nanometer with the standards. So I can we can tell the guarantee 100 nanometer, 2 nanometer you can get. If there's still the old equipments, 200, 300 nanometer, sometime 1 micron only they can give the resolution. Then FESM is coming to the picture. The resolution ultimately you can get 0.8 nanometer with respect to the standard. Don't come with a 0.8 nanometer sample and you want to do FESM means it's not possible. Metal based sample we can tell plus or minus 2 to 3 nanometer, definitely we can get the resolution for metals. And metal oxides, of course, we can go the resolution of 10 nanometer. Okay, without gold coating or whatever the parameter we are controlling. So 10 nanometer is the real resolution of non-conducting material, and conducting material 3 nanometer we can definitely get in FESM. So when the TM is coming to the picture, if you want to resolve the picture more accurately, there are some core shells are there. Definitely SEM is ruled out. We need to use a technical TM, transmission electron microscope. It's a complementary for SEM. Then with that we can. Okay, and EDS is add-on. SEM EDS also can be done, TM EDS also can be done, but TM EDS, it is much more accurate. Don't focus yourself, only TM can give the image. Crystallographic information, we can get it from the TM. That is the biggest beauty of TM. Okay, so TM we can do mostly for the crystallographic analysis, but I don't know how many people are utilizing it. Crystallographic means what we are doing in XRD. XRD the D-spacing and all, we are calculating, but here you can see the D-spacing in TM. That's the beauty of the thing. From there, you can tell what material orientation there, we can visualize the thing there in TM. Okay, so condition for TM, your sample should be 100 nanometer electronic transparent. So if you have some mud or if you have some stone, you can do SEM. But at the same time, you want to go for TM, it is not possible because the condition for TM is the sample should be 100 nanometer electronic transparent. There are many ways are there to prepare the TM sample. TM analysis, TM measurement is 25% only equipment operator job, 75% in the sample preparation. Keep the point in your mind. So maybe in next occasion, then I'm sure I can share. Because I completely agree. I am trying to tell some techniques. I don't want to compare all the things. I'm just taking two things, XPS and SEM. Then why we need to go on which condition you have to choose. With that, I'm just ending this. Quickly, I'll just show the findings. SEM, how does it work? Then you just see over here, it's electron source. When you apply a filament heat, filament current, what will happen? There will be some emission. Of course, we need a lenses, magnetic, electromagnetic lenses. There are two lenses are there. One is a condenser lens and the objective lens. When that condenser lens to form the beam, to demagnifying the beam to a couple of stages, objective lens generally we are using to focus your beam. Once the guy is focused on your sample and it is generating some signal that will be imaged over here. So you can ask what is the role of what is the name defined? Scanning electron microscope. When the beam generation formed demagnified, objective lens focused on your sample, how do you know where the signals are generating? Okay, so in that aspect, above your objective lens, there are some important parts called scanning coils. So the scanning coils, it's a raster scan pattern. So which is raster scan means how you are writing in your notebook from left to right, top to bottom. That pattern is called that raster scan. This raster scan pattern, it is aligning the beam to read in which manner. That is the concept of SEM. That is what, because of the scanning coil only, we are calling this equipment as a scanning electron microscope. So that gives that surface morphology or topography information of your samples. AFM, SEM, don't confuse. AFM, it's just a topographical 3D view we can get, but it is only localized region. So 17, 19 micron or 100 micron, that is that area you can scan. SEM, we can play around in millimeter to that nanometer level. Okay. So 3D can be done directly in AFM. 2D image only you can get in SEM, but you can do 3D if you want, if you have any software. So the bottom line is the resolution is determined only by the beam diameter. If you use a normal tungsten filament, as I told, 50 nanometer is the resolution. FESM means probe tip, it seems it is very less. You can able to achieve high resolutions. Okay. So these are some images, FESM images, cross-sectional images I taken. This is almost all I taken. Okay. I'm really proud. So this is some of the thing I made it for the open day for the kids. So why, in the sense, with this I will end. Kids coming and asking, because nowadays the kids are like, they are very knowledgeable. Okay, so you know very well. So we can't answer most of the questions like that. So how to convey the message to the kids? What is the electron microscope? Why we need it? Means I can't tell the beam coming and hitting electrons are scattering and backside electron, second electron. They will run away. They will not stand there. Okay. Like we have some evidence this ant. So we have we image the tree ant. This is the jaw of the ant, and this is the eye. This is the honeybee. It's a wing, the antenna of the honeybee. This is the drosophila. This is the hair. So hair sample we carried out. So this is the kind of exhibition we did, and this is some biological samples also we carried out. Apart from the normal thing, we can do many in situ measurements in SEM. Maybe next time when we meet, then we will. So this is EDS analysis. This is cathodoluminescence. I have not having some time to touch. It's a complementary for PL, photoluminescence. So we will get the emission wavelength of the things. Okay, so with the corresponding that emission wavelength, we can get that band gap of your material. So cathodoluminescence, it's a complementary for PL, photoluminescence, what you're doing in Nano. Okay, so there are many techniques are there. Electrical characterization. There are so many, but anyway, I can. So last but not least, then I would like to acknowledge my team. Without their support, definitely we cannot run this facility for more than 10 years, because IIT Bombay, we have the same facility, but at the same time, due to funding issues, there are many issues, and we lose the many people. And we cannot run the facility, many of the facility in many places. Even IIT Madras also, they started, but they're really wondering. So they're always keen to see that how we are maintaining the people, because facility management is one thing. Second thing is the people management. So we are really proud, we are managing both in our center. So that's why, from last 10 years, we are, we have same team. So most of the people, senior people, they stays here, and we are holding them for some better applications. Okay. Thank you so much for your attention. So I'm apologies for your because I took nearly around 1 hour 45 minutes. So I hope something you got from my side, and if you're not getting, no problem, I'm reachable, so you can catch me anytime. So I would like to address some of the questions if you have. So maybe Dr. Rajesh sir can coordinate.
Yes, sir. Dear participant asking some questions. This is a open discussion time.
Tamil open. You can ask Tamil kuda neenga kekkalam, thappu illa, kelunga.
Dear participant, any questions?
There are two ways are there. There is no question means if they understood all, then there won't be any question. They are not understanding anything, there won't be any question. I don't know how I can take. Maybe it's a discussion actually. So come on, it's a discussion.
Yeah.
So it's a kind of interaction. It is not a one-way learning. It's not a class. Okay. So
good morning, sir.
You can ask any questions.
Sir, one more question. Yeah.
Hello, good morning, sir.
Good morning, sir.
Thank you,
sir.
Sir, any repair technique is there, sir? For example, in mass production, some repair will occur. For example, in nanotechnology,
yes, sir.
Repair technique is there. For example,
repairing means
fracture occur means, for example, we are doing welding now.
Okay.
Metal, to join the two metals, we need welding. Like that, nano material, how we join, sir?
Okay, so very good question, sir. Actually, so how we can weld? Okay, so we have some lithography techniques. So ion beam and electron beam lithography techniques are there. So there, for example, 2 nanowires are there. If I want to, for example, we are going towards a micro nano techniques. So if I have some nanowire, I want to do some contact pad. So with the help of ion beam lithography or electron beam lithography, we are making a contact pad in that. If any cracks are there, for example, reverse engineering. So many times, the people from SanDisk, I should not tell, many things are confidential. So WD and SanDisk and all, they will come here. So they will come with a pen drive, which is not working condition. So they will come here and they will do some circuit editing. So that technique also we have. So since the mechanical thing, we have universal testing machine is there. For example, something you are making that tensile compressive studies also we can make. And in situ measurements also can be done. Nano indentation we are not having, but we have in the campus to quality check of your material. So our peeling test, if you deposited some thin film, we can do some peeling test as well. But as you ask, what we can do for the nanomaterial welding, so we have some lithography technique to weld the samples. Either we can do connection or we can do etch out. By mistake, some deposition technique that people they made, so it is shorting, that short circuiting that material device. So we can do some etching. We can do some etching the particular region in the nanometer precisely. That also can be done.
For chemical, we can go for chemical, no, sir?
That we need some precise etching, sir. That's what litho is one of the thing. So there photolithography is there, electron beam lithography is also there, ion beam is also there, FIB we used to call focus ion beam. So there we need a mask or something we need a photoresistive kind of thing. Sorry. So if you are coming with a device, failure device directly, so electron beam lithography or ion beam lithography, we can directly load and we can cut out some region. And if you want to, large regions are there if you have some particular mask, because we need to design the mask. Mask itself will cost a couple of lakhs. So that mask, if you have for your precise design, or if the vendor is providing that, sometimes the customer is providing their own mask, they know that region. There, we can go for the chemical etching or dry etching. There are many things are there. But if you're not having any mask, you're not having anything, directly you can go to that focused ion beam technique. There, we can do some circuit editing in the nanometer to the micrometer.
Okay, fine, sir. How inspection is done? Okay, fine, sir. How inspection is done, sir?
Again, we have to do some testing. See, once you've done the welding, we have to check the quality of the material with the electrical characterization. It's step by step. So once I etch out something, again it is going to other testing to qualify the thing. In case if it is working, fine. If it is not working, then we have to start from the scratch. From the fabrication, we have to do a lot of activities.
Okay, sir. Which one is best, sir, for characterization technique?
Which means
it is universally accepted standard. Standard is there now. Universally accepted standard is there now.
Exactly, sir. One thing I want to share, what in the sense, none of the characterization technique alone can solve your problem, because it's all complementary each other. So you know very well. So even for example, if I'm doing SEM, zeta particle size analyzer alone, so I cannot conclude my particle size. So we need to go for some other different techniques to find out. So whenever you are coming with some problems, for example, you are a mechanical person, so generally so we need to go with some UTM. So universal testing machine, might have seen that universal testing machine is one of the way, and followed by the indentation. For example, you are coming with a material hardness thing, you want to find out the indentation. The nano indentation is there, pico indentation is out there, and AFM. So surface roughness also we can do with the profilometers. So there are many complementary techniques are there. Then we can do it one by one, and we can conclude as a project.
Okay, sir. Yeah, sir. Any acceptable error is there, sir? For all this,
definitely it is there, sir. Definitely it is there. As I told, for example, less than 1%, it is not possible in the EDS. Similarly, there are some error percentages are there. So acceptable error is 2% if the equipment is calibrated. If the equipment is not calibrated, I don't know. I don't want to comment other places what and all the facility they have, whether they are doing calibration or not. But at the same time, if you are properly maintaining your tool health and other things and all. Of course, the error percentage 2 bars, it is there. Acceptable 2 bars, 2%.
Okay, sir, fine.
Sir, I have a doubt.
Yeah.
Hello.
Yeah, please go ahead.
Sir, sir, if the source material has some impurities left, and because of which when we are doing the characterization and we are getting a graph which is similar to some a component or element which is previously present, then sir, how would we identify that it's not because of the not because of the impurities, and it's just because of the element these characteristics are shown?
It's a very good question actually. So what I'm trying to tell, how do you identify the impurity? Because of the main material, impurity playing a role. I mean, that's a question or not? Hello. So I think I hope that is the question. So if you have some material you are doing some doping, so how do you ensure that it's playing off the impurity or playing off your main material? So the answer is you have to do some electrical characterization. So whenever you do some material property testing, for example XRD you are doing. So when you do XRD, you will get that intensity variation of your plus. You have to take a pristine material. For example, zinc oxide means zinc oxide you take a pristine material. So where the peak portions are there. Then when you are starting and coming with your doping material, then you can see that there is some variation in the intensity or the peak portion. One thing. Second thing is my suggestion, go with the electrical characterization. there, like that DLTS techniques are available actually. So the deep level transition spectroscopy technique and Hall measurements. So pristine material, you do the Hall measurement, Hall mobility, and then you go for your impurity material. Are there, you can easily identify that mobility or whatever thing you're doing, the concentration of impurity playing a big role. Electrical characterization is a solution for it.
Sir, Professor Sankar Narayan writing some question asking, sir.
Yes, please, sir, please.
Sir?
Sorry, I didn't see.
Sir?
Sorry, the voice is not audible.
Hello.
Sir? Okay, sir. Sir, any others? Kavya from Kavya.
Maybe Professor Shankar Narayan, sir, you can put your questions in the comment section, sir. Some chat box in there. Then somebody can read for you, please.
Hello, sir.
Sir, please.
Sir, am I audible?
Yeah, you're audible, please.
Okay. So very interesting talk. So I have a question. Query. I am fabricating metal surface in nanometer range.
Okay.
So for currently I have designed. So I wish to fabricate that. So through INUP, I believe sense is accessible.
Yes, sir. Actually, so I think you can reach us in two ways. One is MHRD. Now INUP, it is rephrasing this the word called MHRD program. So there, you can reach us. What and all the proposal you have, then you can apply, and the facility you can utilize free of cost. So ETAD, everything completely you can get it through the program. I forgot to mention that people who they are really interested, you can come as a MHRD user and you can use the facility. If your project proposal is accepted, then you can. Second thing, you can always welcome as an external academic user. So that can be done. That is the easiest way to reach us. Maybe MHRD program, it will occur I think in this pandemic situation we are not organizing any MHRD program. So otherwise 2 months once we have a program, and we used to call the participants for workshop and hands-on and all. Hands-on means definitely will not get opportunity to some hands-on and all, but you will be with our facility technologists. You understand the process and many things. Okay, so MHRD program, of course, you can come. If you want to come only for your device electrode deposition. So right now there are many restrictions out there. You cannot be physically present over here. I don't know up to how long we need to, because pandemic thing very well. So it's a COVID issues we are not allowing anyone physically. But if you want to deposit something if you are already MHRD or INP user, you can send the sample. Then I can share that the people contact details. Then through them you can approach and you can get your work done.
Sir, Professor Sankar Narayan is waiting, sir.
Yeah, yes, Rajesh, can you hear me, Rajesh?
Yes, sir. Yes, tell me, sir.
Yes, very good. Yes, Professor. Yeah, please.
Sir, really thank you. Sir, really thank you for presenting this technical data.
It's my pleasure to join with you all. Actually, it is a really wonderful talk given by this Dr. Vararajan from IIS Bangalore. Okay, actually, sir, can you comment on this angle resolved XPS, where it can be used? Because even though we are having XPS machine in our center, but none of the samples are coming for angle resolved XPS.
Okay, sir. Okay, sure. Definitely I will, sir. XPS, I think you understood that what generally we are doing it. Angle resolved XPS, it's a special mode actually. So one of the mode people they are having in their equipments. So what it will do means, for example, if I'm coming with a 2D materials, so graphene monolayer or some multi layers I'm bringing. So the thickness of the layer is ultra thin film. So 3 nanometer, 4 nanometer is there. My substrate is also some carbon based material or some silicon. Silicon is a substrate I'm taking, and I have some carbon deposition or exploited or something I did. So 3 nanometer and below that silicon only more region. So when I'm exposing that beam and photoelectrons are collecting, more intense I will get for silicon than the carbon what I'm looking. So that's one thing we can see in the normal XPS. When you do the angle resolved XPS, what I'm doing, so this is my stage, means I'm just tilting the stage by an angle. I'm just beam, it is coming and hitting, and I'm controlling the beam penetration only to the surface region. So angle resolved XPS only for the 2D materials. I can tilt the stage by 6 degree, 50 degree to enhance that surface material intensity than your substrate. That's what like now we're using angle resolve for 2D materials.
So that means you want to increase the resolution of your peak by changing the angle of your specimen?
Exactly, sir. So we need to, for example, SiO2 on SI. SiO2 is there. It is like 5 nanometer. I think I can show you that slide. Then maybe if it is visible, then it's great, sir. Yeah, you just see this is the slide. When you are at 0 degree, you can just see, sir, that silicon 0 degree, that the silicon bonding peak is very high. And my intention to see that 5 nanometer of silicon dioxide or native oxide of silicon, which is our silicon dioxide on my surface. So when I'm doing started to tilt, I can get such silicon bonding oxygen than that silicon bonding. So this is the evidence when you tilt the stage, and I can expose more onto the sample surface, and I can eject the photoelectron only from the surface. Yeah.
So then is it possible to correlate this angle with the crystallographic axis of your sample?
Exactly, sir. We can. So we have some angle calculations. So that with that calculation, then definitely we are correlating it. So we have angle resolved UPS measurement as well as also to find out your valence band portion directly. So angle resolved UPS, AR UPS also can be done. So we have a calculation. Then sure, I can share.
Okay.
Because it is correlated. Because ultimately, what we are trying to do, then we are ejecting the photoelectron from your specimen surface. That angle of incident, that's what you were asking. So incident angle and the photoelectron ejection angle also matter. So if it is 0 degree means 9 degree is a vertical is the angle of photoelectron emission. But when you're tilting, then of course we have to do the corrections. Okay. That can be done, sir.
Okay, then. Thank you. Thank you so much. Bye.
Thank you, sir. Yeah.
Sir, kindly share your contact information.
Okay, sir. You want to share right away, or maybe somewhere chat box is there? I can share my mobile number.
Sir, sir, one question from YouTube. Kopala question. It was very. Sir, what type of substrate to use to take the image for biological sample in AF and TIM? Any special substrate, please recommended me, sir.
Okay, sir. So biological sample generally wherever you go, they will not allow because of contamination. Tip contamination will be there. TM equipment, it seems there are many contamination will occur. So substrate means you can take any substrate, any conducting substrate, flat surface. Because if it is something fluxy substrate you are taking, for example, aluminum foils you are taking for drop testing your biological sample, or a glass slide. When you're taking a glass slide, first you measure the roughness of your glass slide in AFM. Because the roughness value it is more than 40 nanometer, 50 nanometer, and your material roughness is 4 nanometer, 5 nanometer. You are compensating with both. We have to compensate with both. So substrate should be flat. It is good for more how much roughness you can able to reduce. That is good for the AFM analysis. And TM means there are specially designed TM are there. It's a cryo TM and all is there. Normal TM generally they will not allow because 200 kV is a beam fixed for your general TM, 200 kV or 300 kV. So generally biological sample, how they will prepare means they have a TM grid. I think, when you go for the TM, there won't be any substrates. There will be TM grids are available. So 200 micron mesh, 300 micron mesh. So there, you take your, diluted solvent, biological something cell or whatever the thing. Do drop testing, allow it to dry. The TM grid alone, you have to go for your TM analysis. So conditions apply, as I told already, 1 micron, 2 micron thick your shell or something that features are there. No need to go for TM. So you can prefer the SEM to finish it out. So the transparency is a matter in TM. But how to prepare the substrate means the TM grids are available. That is the answer. AFM means the roughness of your substrate also matter. So when you prepare your sample, flat surface, it is much needed. Okay, so you can choose my preference, what I will prefer means silicon based substrate. So highly polished silicons are available, and if it is possible, you can buy or highly polished metals or something which is not disturbing your measurements. Definitely you can.
Sir, one more question.
Yeah.
Which one characterization technique is economical, sir?
Okay. Characterization techniques in terms of what? See, electrical measurement means when I was doing my MTech, then I carried out some of that Kelvin probe. What is that Kelvin probe, I think? So to measure the Hall measurements, one end it is hot, another end is a cold. So there, I measured the deflection of the voltmeter. I can tell whether it is a P type or N type. We can do that. So that is one of the cheapest thing. I can tell. Another thing, what and all you can able to design. Of course, you cannot see. To be frank, none of the characterization technique equipments what we have in our lab. none of them are made from India. So all the things are imported for some reason. So we are not up to that level. So if you want to make some other thing in your own lab, as I told, the electrical characterization thing, simply you can make your one, but we have to compensate many of the things. So with my knowledge that definitely apart from the electrical characterization, assembling the thing, none of them you can able to make your own. So portable or some small cost. See, for example, there are two things. See, you have to sacrifice on your own results. So results are fine. Something if I'm getting fine means the cost will be low. Results are like high quality or looking mean the cost also will be there. So the least equipment what we have in our characterization division is 1 crore. That is zeta particle size analyzer. So the cost of the equipment is 1 crore. So we are spending to get some good quality results. That is what the cost is playing a role. SCM cost 3.5 crore to 4 crore we are spending. So to get the best results. So it's a one-time investment. So it is not. It's a kind of silk saree. I think buying a silk saree is easy, and maintaining it is it is very tricky. So it's a kind of thing. So economic characterization it is not there, sir. Actually, so my suggestion: don't try to buy equipment and try to send the sample for your characterization. Economic means it depends on that. As I told, they have a lower end equipment. They will charge 50 rupees per sample. And if it is a higher end equipment, they will charge 5,000 per sample. So it depends, what quality you are getting. Accordingly, you can check in on offline, because see, what my intention is, it is not required, recommended. Always you have to come here, because you are there in your place, and here we are. It is not recommended we have to come, but try to understand the concept where and all it is available nearby. I think I would like to share, there is some program called iSTEM. So iSTEM, it is it is our department is the coordinator is Dr. Sanjeev. So what they are trying to do means it's a kind of Ola Uber kind of app. So when you are trying to book some Ola cab or Uber cab, so where and all the nearby things are available, you can get it in the app. Similarly, this iSTEM thing, you just try to install the app in your mobile. So the iSTEM app, it will tell where and all the nearby characterization facilities are available. Of course, the cost, it may not be there, because we need to compare apple to apple instead of apple to orange. So my suggestion, 50 rupees also will get the same results means, 5,000 also getting the same results means, you have to evaluate the things before you are going. So that's the bottom line. Cheapest means I cannot comment which is the cheapest and higher end, but quality matter. What we are getting output, that I can compare and tell if needed. Okay, so maybe you can catch me offline, then sure I can help you where it's available, where and all it's available, you can access that things. Yeah.
Sir, one more question regarding, can you give the scaffolds techniques with nanoparticles?
Scaffold thing, what do you want to do that? Scaffold layer deposition or what?
Scaffold
nanomaterials.
Yeah, nanoparticles.
Okay, sir. Actually, it depends, sir. See, if you want to try to make a scaffold for your thing, then of course we need to go for that thin film. You have to make it as a thin film. For example, scaffold means something which is not affecting the thing. See, for example, if I'm depositing some organic LED or solar cell or whatever the thing, so some layer is there. Just I want to protect the thing just for some other what and all I'm doing. So that scaffold layer, it should be uniformly decorated onto your sample surface. So then only it will solve the problem. There are many things are there. If you're looking the perovskite material, aluminum oxide is there, Al2O3, and any oxide material will be a scaffold, titanium dioxide, and there are many things are there. But the matter, what I'm trying to tell, it is a matter of how you are efficiently covering that layer as a scaffold. Any materials are there, but it's a matter of that what technique you're using to make it as a scaffold, that particular material on your device.
Please participate. Any questions? Sorry, we have no more questions. Really, very
sir,
thank you.
I have
Pardon me?
a question.
Yes, sir. Continue, sir. Continue.
Pardon me?
Sir, I am designing a structure which has a SiO2 substrate.
I'll come to you just a minute.
Si carved
Just a
the
minute.
surface. So it is in nanometer range. And it has a cut in around 50-60 nanometer around range. So what characterization facility we should use to surface profiling that our structure got correctly fabricated?
Exactly. So it's a good question. So if you have a trench 50 to 100 nanometer, a preferable thing you can do a profilometer. There are profilometers are there, non-conductive profilometer, optical profilometer is there. It's a complementary. for AFM. AFM is one of the technique you can find out, and you can cross verify with SEM, then you can conclude your results. So whether the trenches are there in all the region, vertically you can see, and horizontally you can mount your sample, and you can do that. SEM is one way. Second way is AFM to conclude that what is the depth of your trench, how the wedge it formed, it is clear cut or it is forming as a wedge and all. AFM you can get. Profilometer is a complementary for you to conclude. Start with optical profilometer, lower end equipment, go with the AFM and SEM, conclude it.
Okay, sir. So these structure can we fabricate using lithography or?
Of course, you need a litho for this because 50 nanometer, of course, you need to use electron beam lithography.
Okay, sir. Thank you, sir.
Okay, thank you. So Professor Kunjumana madam is there, so.
Yeah. I am here.
Yes, very good morning, madam.
Very good morning. And
yes, thank you.
I express my gratitude to Dr. Rajesh and all the organizations for arranging the talk of Varadu sir. It's really.
Thank you, madam. Because you are my collaborator, you know very well. So we had a direct discussion as well.
Yes. And the research paper is also ready, and it's a lot of gratitude to you, Varadu sir, for collaborating with everybody, not only with me.
Thank you, madam. With pleasure.
Whoever comes to Indian Institute of Science, you are very much willing to help everyone and helping the entire scientific world.
Thank you, madam. Thank you so much for the feedback.
So nice presentation and covering all the aspects of characterization. Okay.
Thank you.
So nice. We'll meet soon. Okay.
Thank you,
ma'am. Thank you, ma'am.
Okay, thank you. Thanks a lot.
Any other participant asking questions? Any others? Sir, a really nice presentation regarding this micro and nano particles. Now, going to tell you the vote of thanks. The Honorable Chief Guest, respected principal, and all the participants, my privilege to propose the vote of thanks on this occasion. I wish to express my gratitude our management for giving us an opportunity on organize this event. I am very grateful to our principal, Dr. Nagarajan, and self-managed director, Dr. A.M. Dhoni Melvin, director, providing encouragement, support, and conduct this technical meet. And I really thank to today of the hero. I would like to extend my special thanks to Dr. Varadaraja Perumal, the technical manager, for wholeheartedly accepting to the speaker for today technical meet. I would like to my special thank to Professor Dr. Muthusendal Pandian, SSN College, Chennai, and Dr. Raji Narayanasamy, Professor in our college, and also Dr. Selu Rajan, Adityanar College, Associate Professor for whole this program support. Finally, I heartily thank all the participants for their active participation in the event. Really thank you one and all. Thank you, sir, for your valuable, wonderful session. Thank you very much.
Thank you, sir. Thank you so much for the invitation.
Bye, sir.
So,
thank you. Bye.
Bye.
Thank you, yes, sir. Very nice presentation. Thank you so much.
Bye.
Thank you, sir. Please, audience participants, please feedback link in the chat box. Sir, good morning, sir. Yes, sir. Abdiya. ஆமா அந்த ப்ரோக்ராம் முடிஞ்சிச்சா சார்? இன்னைக்கு தான் 9 to 10 9 to 12 முடிஞ்சிருச்சே சார். செமையா இருந்துச்சு சார். சார் அந்த லிங்க் உங்களுக்கு இன்விடேஷன் அனுப்பியிருந்தேன்ல, அதுல இருந்திருக்கும்ல சார். இது வந்து கூகுள் ஃபார்ம் நான் உங்களுக்கு தனியாக அனுப்பிவிட்டேன். உங்களுக்கு லிங்க் வந்து முன்னாடியே சரி வந்து வர, சப்போஸ் வர முடியலன்னா இதில் வந்துருங்கன்னு உங்களுக்கு அனுப்பிவிட்டேன். ப்ரோக்ராம்ஸ் ஓகே. அது நிரப்பி அனுப்புங்க, நிரப்பி அனுப்பிவிடுங்க. ஓகே சார், நல்லா இருந்துச்சு சார். ஓகே, தேங்க்யூ சார், தேங்க்யூ. அவ்வளோதான், ஒரு நாள் தான் சார். இல்லை சார், நான் ஒரு 1.5 hours தான் சார். அது வந்து 5 லிங்க்னா வந்து உங்களுக்கு நீங்கள் சப்போஸ் வரலைன்னா மேலும் மேலும் வர்றதுக்காக நான் அனுப்பியிருப்பேன். அப்படி இருந்து உள்ள வரல. எஸ் சார், எஸ் சார், எஸ் சார். சார்
ஃபீட்பேக் அனுப்புங்க சார்.
எஸ் சார். இல்லை அது ப்ரோக்ராம் முடிஞ்சிருச்சு. 2 hours ப்ரோக்ராமு. பரவாயில்ல சார், ஒன்றும் பிரச்சனை. நீங்கள் சீனியர் கோர்ஸ் சார், ஒன்றும் பிரச்சனை சார். தேங்க்யூ சார், தேங்க்யூ சார், தேங்க்யூ சார். ஆமாம், கண்டிப்பாக அனுப்புங்க சார். என்ன சார் சொல்லிட்டீங்க, அனுப்புங்க. ஏன் கண்டிப்பாக உங்களுக்கு இல்லாத அப்படி உங்களுக்கு இல்லையா சர்டிஃபிகேட்டே வேஸ்ட்டு. அனுப்பிவிடுங்க சார், அனுப்பிவிடுங்க
சார். ஃபீட்பேக் லிங்க் கிடைக்குமா சார்?
எனக்கு தான் வரும், நான் தானே கோஆர்டினேட்டர்.
சார் ஃபீட்பேக் லிங்க் அனுப்புவீங்களா சார்?
எஸ் சார், எஸ் சார்.
ஹலோ சார்.
கண்டிப்பாக
இதில் மெயில் அனுப்புவீங்களா சார்? இல்லை இதில் போடுவீங்க, சாட்டில் போடுவீங்களா சார்?
சார்
மெயில் அனுப்புவீங்களா இல்லை சாட்டில் போடுவீங்களா சார்?
சாட் போட்டலாம் சார். ஆல்ரெடி போஸ்டட் சார் சாட்ல ஃபீட்பேக்.
வரல சார். இல்லை வரல சார், இது வரைக்கும் வரல சார். எல்லாரும் கேட்குறாங்க சார்.
இல்லை சார், யூடியூப்பா அதர்வைஸ் சார் ஜூம்
சார். எவரிபடி ஆஸ்கிங் சார்.
சார் வெயிட் சார். ஆல்ரெடி
நோ சார், எவரிபடி ஆஸ்கிங்
சார். 10 டைம்ஸ்
வரல சார். நோ சார், ஜூம்க்கு அனுப்பல சார்.
சார் ஜூம்ல வரல சார்.
ஓகே வெயிட் சார். now okay?
No sir.
Sir, the Zoom it is not available.
ஆமாம் சார், ஜூம் ஃபீட்பேக் லிங்க் நாட் அவைலபிள் சார்.
Sir, 1 minute. Sir, please see that chat box, sir.
Yes sir, we are seeing the chat box only sir.
Chat box la illa sir.
Now?
Illa, no.
Sir, okay sir, no problem. I will post a WhatsApp group, no problem.
Okay, fine.
Okay, thank you all participants. Thank you. என்ன ஏன்னா யூடியூப்ல நான் நிறைய போட்டு விட்டேன். அது என்ன செய்யணும்ப்பா? நான் போட்டுட்டேன், அப்படியே போட்டுட்டேனே. வாட்ஸ்அப் அனுப்பியிருக்கேன். மேடம் ஓகே ஓகே. ஓகே மேடம்.
உனக்கு இன்சைடிங் இருக்குடா. எனக்கு போன் வந்துட்டே இருக்கான், இரிட்டேட்டிங்கா இருக்கு, மாத்துங்கிறா. அவளுக்கு என்ன
போன் வந்துட்டே இருக்கு. யார் கால் பண்றா? அது எடுக்குதா?
மேடம் தான் கால் பண்ணுறாங்க. தண்ணி வேணும், வெளில கூட தண்ணி குடிக்கணும்.
ஏன் குடிக்கல?
நான் எதுக்கு குடிக்கணும்? தண்ணி காட்டு இல்லாம தண்ணி குடிக்கிறது.
நான் இது தண்ணி, நீங்க தானே இப்ப தண்ணி காட்டுறீங்க, சொல்றது வந்து செய்யுது.
ஒரு 2 வாரம் எக்ஸ்ட்ரா அங்க போய் எவ்வளவு கூட்டத்துல நிக்க வேண்டியதா இருக்குதுன்னு பார்த்து பண்ணிட்டு வரேன்.
சரி, இப்ப என்ன குழம்புன்னு சொல்லுங்க.
நான் தெரியாது.
எதுனால வந்து சாதம் மட்டும் தான் அடிச்சிருக்கோம்.
சரி, பரவாயில்ல. நான் சார் தயிர்
காய் எதுவும் இல்லை, ஒரே ஒரு கத்திரிக்காய் மட்டும் தான் உட்காந்துருக்கு. வாழைப்பூ இருக்கு, வாழைப்பூ நாளைக்கு தான் செய்யணும். அது எடுக்க லேட் ஆகும். எடுத்து தந்தா நான் செய்வேன்.
ऑलरेडी खत्म हो गया ना?
பாலா பேசுறேன். இப்பதான் கடைக்கு போயிட்டு இப்பதான் வந்தேன். இப்பதான் வந்து சார் பார்த்தேன். எல்லாரும் பேசிட்டேன் மேம். இல்ல நான் வந்துட்டேன் மேம். வந்துட்டு இப்பதான் வந்தேன். பாப்பாக்கு இன்னைக்கு ஏதோ ஃபீட்பேக் சொன்னாங்க. ஸ்கூல்ல வந்து 16ஆம் தேதி ஸ்கூலுக்கு பசங்க அனுப்பிலாம் வேணாமன்ட்டு ஸ்கூல்ல வந்து லெட்டர் கொடுக்க சொன்னாங்க. வந்துட்டு அது அங்க போயிட்டு அவங்க ஸ்கூல்ல லெட்டர் கொடுத்து 16 ஸ்கூல் வர சொல்லிருக்காங்களா மேம் ஸ்டூடெண்ட்ஸை? அதான் சொல்லியிருக்கேன். அங்க எல்லா பேரண்ட்ஸ் அதான் சொல்லிக்கிறாங்க ஸ்கூலுக்கு. சார் ஓஹோ சரி. ஓ நான் இப்பதான் சொல்லிட்டு லெட்டர் கொடுத்துட்டு அங்க ஒரு மேடம் இருந்தாங்க, அவங்க கிளாஸ் டீச்சர் இருக்கு. அவங்கள்ட்ட பேசிட்டு இருந்தேன். ஸ்கூல் வந்து ஒரு ஆவரேஜ் ஸ்கூல் தான், அதனால கொஞ்சம் ப்ராப்பரா இந்த சானிடைசர் மாஸ்க்லாம் அதெல்லாம் ப்ரொவைட் பண்ண மட்டும் தான் பண்ண முடியும். என்னக்கா நான் ஜனவரி எப்பதான் அனுப்புறேன்னு சொல்லிட்டு வந்துட்டேன். லெட்டர் எழுதி கொடுத்துட்டு வந்துட்டேன். அங்க எழுதி கொடுத்த வந்தேன்னா கண்டிப்பா முடிச்சு வாரத்துக்கு லேட் ஆச்சு. கொஞ்சம் ஏடிஎம் பெட்டி இப்பதான் வந்தேன், 2 பிஸ்கல் இருந்தது. ஓ ஓ ஓ பசங்களுக்கு சின்ன பசங்க இம்யூனிட்டி இருக்காது. ஸ்டாஃபுக்கு நல்லா 40+ வேற, அவங்களும் இம்யூனிட்டி இருக்காது. ஸோ கொஞ்சம் கஷ்டம்தான். அதான் எழுதி கொடுத்து வந்தேன். சார் சொல்லுங்க மாமி, சொல்ல வந்தீங்க. சரி சரி, நான் என்னோட பசங்க போட்டு கண்டிப்பா மேம். சரி சரி சரி.
मेरा नंबर बताओ तो, फोन नंबर.
சரிங்க மேடம் சரிங்க மேடம். இப்போ வேலை முடிச்சிட்டாங்களா? சரி சரி, எனக்கு இன்னும் வரல. அவங்க அனுப்பிச்சு இப்போ நேற்றா ஒரு பேரண்ட்ஸ் மட்டும் மிஸ்ஸிங் இருந்து அந்த பேரண்ட்ஸ் காலையிலே பேசிட்டேன். அது மாதிரி அவங்க வந்து ஆமாம் பில்லி தனலட்சுமின்னு நினைக்கிறேன். அவங்க அப்பா வந்து ஏதோ காலேஜ் ஏதோ ஸ்கூலில் பிரின்சிபால் போல இருக்கு. அவர்கிட்ட பேசினா பட் பொண்ணுகிட்ட ரீச் ஆகல போல இருக்கு. அப்புறமா போன பிறகு அப்போ காலைல பேசிட்டேன். எல்லாரும் 14 பேருக்கும் பேசிட்டேன், எல்லாரும் பேசிட்டேன். அப்படிங்களா? சரி சரி சரி. ஆமாம் கடைசியில் ஆமாம். அவங்க என்ன சொன்னாங்க, உங்களுக்காக தான் மொபைல் ஃபோனு, புது நம்பரு, மொபைல் ஃபோனு எல்லாம் வாங்கி இப்போ தான் புதுசாக பாப்பா ரெடி பண்ணிட்டு இருக்கேன், அதனால தான் லேட் ஆச்சு அப்படின்னாங்க. லேப்டாப் இல்லை. ஆமாம். 1-2 பேரண்ட்டு இன்னைக்கு